We're live now.
Okay, thank you very much to all the participants for joining us. It's with great pleasure that we give you the welcome to the International Congress of the International Community of Mathematicians from Latin America, ICMAM Latin America 2026. We had with us the authorities of ICMAM Latin America and also Professor Inaku Nakajima, President of the International Mathematical Union. So, we are going to start with some words and a speech from Karina Navarro Gonzalez, the President of ICMAM Latin America. So, Karina, please go ahead.
Yes, thank you. Will you hear me well?
Yeah.
Okay, great. Good morning, good afternoon, and good evening to everyone joining us from different parts of the world. Dear speakers, colleagues, students, participants, and friends, it's a real pleasure to welcome you to the ICMAM Latin America 2026 Congress. Thank you for being here. I have had the honor of serving as president of ICMAM Latin America since 2025. This has been a very meaningful experience for me, but it has not always been an easy one. During the past few months, I have faced several difficult challenges in my personal life. However, these experiences have also reminded me of something very important: the value of teamwork. This Congress has become a reality thanks to an extraordinary team, people I consider not only colleagues but also friends. I would like to express my deepest gratitude to Andrea Vanessa Hurtado and Pedro Fernandez, and especially to Duvan Cardona and Brian Grajales, chair and co-chair of this Congress. Thank you for your commitment, your generosity, your patience, and the many hours of work you have dedicated to this community. ICMAM Latin America is not only about organizing conference, it's about bringing people together through mathematics. One of our main goals is to share important developments in mathematics and to give greater visibility to the work being done in Latin America and the Caribbean. Latin America has a rich and diverse mathematical community. Our responsibility is not only to produce excellent mathematics, but also to make sure that this work is seen, discussed, supported, and passed on to the next generation. A good example of this is our most recent editorial project, Mathematics in the Caribbean. The volume grew out of the Amates ICMAM workshop for Central America and the Caribbean, and is the result of a valuable collaboration with our colleagues in El Salvador and other parts of the region. For us, the project is about much more than publishing mathematical results. It's also about recognizing the work of researchers in the region, creating connection between countries, and showing the quality and diversity of the mathematics being developed here. I would also like to give a very warm welcome to our invited speakers. We are truly honored that you accepted our invitation. Your work has made important contribution to mathematics, and having you with us greatly enriches the scientific program of this Congress. Through your lecture, we will have the opportunity to learn about recent developments, new ideas, and advanced perspectives from leading experts in different areas of mathematics. To all the participants, and especially to the students and early career researchers, I hope you will make the most of this opportunity. I am very proud to be part of ICMAM Latin America and to work for a community that believes in cooperation across borders. I hope that during these days, we will not only learn new mathematics, but also strengthen the human and scientific connections that make our work possible. Thank you once again for being here. for supporting our community, and for helping us build a more visible and connected mathematical community. Welcome, and I hope you all enjoy the Congress. Thank you so much.
Okay, thank you very much. Those were the words of Karina Navarro Gonzalez, the president of ICMAM Latin America, now researchers at the Weizmann Institute. So, next, I would like to invite Professor Hiraku Nakajima, president of the International Mathematical Union, who will share some words with us. Professor Nakajima.
Thank you very much for introduction. Dear participants of ICMAM Latin America 2026, and also organizer of ICMAM. So it is a great pleasure for me to send my greetings on the occasion of the biennial Congress of the International Community of Mathematicians from Latin America. One of the important responsibility of the International Mathematical Union, and LMU, is to support the development of mathematics in countries and regions where opportunities and resources may still be limited. Mathematics is universal, but access to education, research networks, conferences, and international collaborations are not yet equally available throughout the world. The IMU is committed to addressing these inequalities. Through the Commission for Developing Countries and many other activities, the IMU supports the mathematical research, education, and collaboration in developing countries. However, support from international organizations alone is not sufficient. Equally important, perhaps even more important, are initiatives created and led by mathematicians within each region. A congress such as ICMAM Latin America brings together researchers and students who understand the region's strengths, needs, and possibilities. It helps building lasting networks, give greater visibility to mathematical works produced in Latin America, and enables younger mathematicians to become active members of the both and regional and global mathematical community. I therefore greatly appreciate the efforts of all those who have organized this Congress. In 10 days, International Congress of Mathematicians will begin in Philadelphia. I'm wearing a t-shirt printing the poster of the ICM. So I'm delighted that so many mathematicians from around the world will participate. At the same time, I'm fully aware that for financial, political, administrative, or personal reasons, attending the Congress in person might be difficult or impossible for many people. The opening ceremony, at which the recipients of field medals and other IMU prizes will be announced, will be live streamed online. All the lectures will also be recorded and made available promptly. I warmly invited you to watch them and to join us whenever you may be in learning about and celebrating the remarkable progress in mathematics which has been made in the past 4 years. I wish ICMAM Latin America 2026 every success and all of you a stimulating and enjoyable Congress. Thank you very much.
Thank you very much. Those were the words of Professor Hiraku Nakajima, president of the International Mathematical Union. Just a couple of comments. We really appreciate EMU for the grants that provide to ICMAM Latin America some years ago that really were very helpful for the organization of several activities, and also to take into account the invitation of Professor Hiraku Nakajima to follow the opening ceremony of the International Congress of Mathematicians that he said will be online, where in particular fields medalists will be known for this year, right? For the
Yes,
mathematical
yes.
community. So very interesting because during this conference also we are going to have some fields medalists giving some talks. So thank you very much. Very good. So I would like then to invite Brian Grajales, Vice President of ICMAM Latin America, to share some words with us. Brian?
Can you hear me?
Yes.
Okay, thank you, Professor Nakajima, for those nice words. And thank you, Duan. Thank you, Karina. And hello, everyone, dear speakers, participants, students, colleagues. It is a great honor to welcome you to the ICMAM Latin America 2026 Congress. As Vice President of ICMAM Latin America, I'm very happy to see our community together once again through our virtual platforms. First, I would like to thank our President, Karina Navarro Gonzalez, for her commitment to ICMAM Latin America. And I would also like to recognize Duan Cardona, chair of this event, for his outstanding work, dedication, and leadership in making this Congress possible. My thanks also go to Andrea Vanessa Hurtado, Pedro Fernandez, and every member of the scientific committee. Organizing an international congress takes a lot of time, coordination, and patience. Many details have to come together, and much of that work happens quietly behind the scenes. We're very grateful to everyone who has contributed. I would also like to thank the Universidad Pedagógica y Tecnológica de Colombia, especially its campus in Duitama, for hosting the in-person activities of this Congress. This Congress brings together different generations, countries, institutions, and areas of mathematics. We will hear about important developments in pure and applied mathematics. One of the main goals of ICMAM Latin America is to create bridges. We want to create bridges between young and experienced researchers, between different institutions, and between areas of mathematics that do not always have the chance to interact. This Congress is one way of building those bridges. To our distinguished speakers, thank you for accepting our invitation and for sharing your work with us. It is a privilege to have mathematicians of such high scientific standing as part of this Congress. To all participants, I encourage you to take an active part in this Congress. This is a valuable opportunity to attend lectures by outstanding mathematicians and to engage directly with experts whose work has made important contributions to their fields. We hope that these days will be productive, inspiring, and welcoming for everyone. Thank you for joining us and for being part of ICMAM Latin America. It is now my great pleasure to officially declare the ICMAM Latin America 2026 Congress open. I wish you all an excellent Congress. Thank you.
Okay. Thank you very much, Professor Brian Grajales, Vice President of ICMAM Latin America, for these kind words. Then it's my great pleasure then to invite all of you to our next plenary talk. We'll start at 15 in Central European Summer Time and in 8 a.m. in Colombian time. The plenary talk of Professor Jung Hu, who actually got the Fields Medal for his contributions to the field of combinatorics. Also, please continue enjoying our scientific program. We're going to have with us Professor Pierre Shapira, one of the giants in the field of algebraic analysis. Later, Professor Luigi Rodino, a specialist in macrolocal analysis. And in the second part of the program, we are going to have an ICMAM presentation at 19. We are going to share all the programs or scientific activities that we have in ICMAM Latin America. So if you are searching to know opportunities, research opportunities, and funding that we provide in ICMAM Latin America, please attend this session at 19. And we are going to close today our program with a Springer presentation where we invite Professor Robinson dos Santos, Senior Editor of Springer, who in particular will talk about the series of book of ICMAM Latin America in Springer and other editorial projects that he's leading. Thank you very much and see you in 15 minutes in the plenary talk of Professor Jung Ho. Thank you very much for joining us. And thank you, Karina Navarro Gonzalez, President of ICMAM, Brian Grajales, Vice President of ICMAM, and Professor Hiraku Nakajima, President of the International Mathematical Union. Thank you very much. See you in 15 minutes.
You.
Good afternoon, Professor Junghao.
Hello, can you hear me?
Hello, yes, I can hear you pretty well.
Hello, Professor.
Okay.
How are
Yes.
you?
Thank you for accept our invitation, Professor.
Okay, my pleasure. Thank you.
So, Professor, let's try to share your screen in the meantime.
Oh, okay. Let me try something.
Yes, sure.
Okay. How about this? This is
Perfect, I think.
I can see it. Yes, perfect.
I can move the pages. It shows well.
I couldn't see the pages moving, but we can try again.
Oh, I am moving now. Can you hear me and see the pages moving or?
I can hear you, but I cannot see your pages moving. But we can try again. Hello, Professor. Hello again.
Okay, I'm trying again. I had a little technical difficulty.
Yeah, don't worry. We
Yep.
have still some minutes.
Now we can see your screen, and also I think we can see
They are,
your change.
yes.
Okay, it's moving.
Yes, they
Yes.
are moving now.
Now it's perfect.
Oh, okay.
Don't worry. Thank you very much.
If you agree, we start in 3 minutes.
Okay.
Are you ready, Professor? Oh,
Yes, I am. Yes.
okay. We start in 1 minute.
Okay.
Okay, I think it's time to start. Okay, hello everyone. On behalf of the organizing committee, we would like to warmly welcome all of you to this morning section of ICMAM Conference 2026. Thank you very much for joining us today. It is a great pleasure for Andrea and for me to serve as chair of this session, this morning session. And for me, and I think we have everyone here, we have the honor to welcoming Professor Jung Ha, one of the most influential mathematicians of our time. It is not just my opinion, I think it's an agree of everybody. Professor Ha is professor of mathematics at Princeton University. He made a groundbreaking contribution to algebraic geometry, combinatorics, and matrix theory. And among his many distinctions, Professor Ha received an MacArthur Fellowship in 2022 and was awarded by the prestigious Field Medal in the same year. It is an immense honor for me and also for our conference professor to have you here as one of our keynote speaker. So, Professor Ha, again, thank you for very much for accepting our invitation, and I think the virtual floor is yours. So thank you very much.
Okay. Thank you for the introduction and thank you for having me. It's nice to be able to talk to you here. So please feel very free to interrupt or and ask questions during the talk. That would be most welcome. And the topic that I want to tell you about today is that of volume polynomials. I understand that the audience today will have a very broad background on many different parts of mathematics, and I think this topic was a suitable one because it touches on almost a little bit of everything from a large chunk of modern mathematics, like algebra, geometry, analysis, and some combinatorics too. And by nature, it's an elementary subject. So if something is not so clear, if I'm going too fast, that's probably my fault. And during or after the talk, you're most welcome to ask for the clarification or further questions. So volume polynomials, it's a class of homogeneous polynomials with real coefficients that has remarkable properties. And at the same time, they possess what I think is a great mystery, and you can ask many crazy questions that are hard to prove or hard to disprove. And I want to share some of those questions. Okay, so you can define the notion of volume polynomials in many different, seemingly different settings, and probably this setting is the most classical one. The setting of Minkowski in a paper where he basically set off the field of convex analysis and convex geometry. So one of the fundamental observations he made on this paper in 1903 is the following notion of volume polynomial of convex bodies. So suppose you have a sequence of convex bodies, C, where each Ci is a convex body in a d-dimensional space. And corresponding to each convex body Ci, you have a variable xi. And for later use, I'll also going to introduce the corresponding partial differential operator, partial I. And by definition, the volume polynomial of this collection C is the function that computes the volume of the linear combinations of Ci's with variable coefficients xi. And Minkowski's observation is that this function of x or xi's is in fact a homogeneous polynomial of degree d with non-negative coefficients. So you can scale your polynomial Ci by xi so long as xi is non-negative, and you can add two convex bodies or more to get another convex body. This is now an operation that we now call the Minkowski sum, and take the volume, and the resulting function is a polynomial. And by definition, according to Minkowski, the coefficients of this homogeneous polynomial gives interesting quantities called mixed volumes of C. So here's a illustrative picture of how volume polynomials are computed. So for example, consider we're in the case of 2 dimensions. So we are in the plane, and suppose we have two convex bodies A and B. And if I want to compute XA plus YB, where maybe A is a polygon and B is a unit disk in my picture, then the volume of the sum will be computed by the shown picture. And the picture shows that the area of XA plus YB is a quadratic polynomial in X and Y. And clearly, the coefficient of X squared is area of A, and the coefficient of Y squared is area of B. And the interesting coefficient, the one in front of XY, will be proportional to the perimeter of A. I hope this makes sense just by looking at the picture. And one of the points that Minkowski made in his early paper is that such a quadratic form cannot be an arbitrary one. For example, if you compute its Hessian, which is the display 2 by 2 matrix, then that Hessian must have a non-positive determinant. And if you write out what the determinant is, and saying that the determinant is non-positive, it becomes an inequality, saying that 4 pi times area of A is at most perimeter of A squared. And this is the famous isoperimetric inequality. So how small can a perimeter be given the area of a convex body in plane? So we're going to meet this property of matrix being Lorentzian, which means that the Hessian has one positive eigenvalue and not two or more. So in general, the realization problem for volume polynomials of convex bodies is to give an explicit description of the set of all degree D volume polynomials in n variables. So if you give me n convex bodies in D dimensions, I get the polynomial. What are all the possible polynomials obtained in this way? Or in other words, can you give me all the inequalities satisfied by mixed volumes of n convex bodies in RD? This is the realization problem for convex bodies. And Minkowski's observation that behind this classical isoperimetric inequality, there is a condition of some Hessian being Lorentzian will be crucial in understanding this realization problem. So formally, I'm going to say that the n by n symmetric matrix Pij is Lorentzian if every entry Pij is non-negative and the matrix has at most one positive eigenvalue. And how to test this Lorentzian condition? There is an analog to the famous criterion of Sylvester testing for positive semi-definiteness, but with alternating signs in the following sense. So a non-negative symmetric matrix P is Lorentzian if and only if -1 to the cardinality of I with the determinant of the principal minor of P labeled by I is non-positive for all choice of row and column indices I. So let's start from the easiest non-trivial case, which was the case of Minkowski. So this is the case of 2 dimensions for 2 convex bodies, where Minkowski's volume polynomial will be quadratic form in 2 variables, x1 and x2. And he noticed that the inequality that he found, saying that the determinant of the Hessian of this quadratic form is non-positive, is actually all the inequalities there can be in this setup. So the theorem is that f is a volume polynomial if and only if the Hessian P11, P12, P22 is a Lorentzian matrix. That's the same as saying that each entry is non-negative and P12 square is bounded below by P11, P22. So that's what we now call Minkowski's inequality. And the realization problem is to decide how this extends to higher dimensions and larger number of convex bodies. So another German lesser-known mathematician, Rudolf Heine, in 1938, wrote a follow-up paper which deals with exactly this realization problem for 3 convex bodies in the plane. So in this setup, my volume polynomial will have 3 variables, x1, x2, x3, and 6 coefficients Pij. And his theorem is still the same characterization is true. So f is a volume polynomial if and only if this Pij, which is the Hessian of f, is a Lorentzian matrix. But he also noticed that the story gets more interesting starting from this point on. So his observation for the next case d equals 2 and n equals 4 is that the same guess no longer characterizes the set of volume polynomials. More precisely, he noticed that this elementary symmetric polynomial x1, x2 plus dot 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 plus x3, x4 cannot be the volume polynomial of 4 convex bodies in the plane, even though its Hessian matrix is Lorentzian. And his reasoning for this elementary symmetric quadratic form is very simple, in fact. So suppose this is a volume polynomial of 4 convex bodies in the plane, then you immediately notice that these 4 convex bodies must be very, very special. For example, each one of them must have area 0, because in the volume polynomial, I don't see any terms like x1 squared or x2 squared. So areas are 0, which in the plane means that every one of the 4 convex bodies must be a line segment. And the fact that all the coefficients of x1, x2, and so on are equal to 1 means that the 4 lines must be equiangular. So pairwise angle between them should be all equal. But clearly, there cannot be such a configuration of 4 lines in the plane. Some lines will have larger angles between them, some others will be short. This is the nature of the dimension 2. This is his argument why this polynomial is not a volume polynomial of 4 convex bodies in the plane. And surprisingly, the realization problem for d equals 2 and n equals 4 remains unsolved as far as I can see. So this is a super duper elementary problem. So you have 4 convex bodies in the plane. What can be their mixed volumes? Find all possible inequalities. I think this is still unknown. Okay, so moving on, G.C. Sheffard in the 60s found a very nice solution to the general case of dimension d, but only when there are 2 convex bodies involved. So in this case, the volume polynomial will be degree d, but in 2 variables. So if you write such polynomial in this normalized form, this 2-variable polynomial is determined by basically the sequence of normalized coefficient pi or pk. And its theorem is that f is a volume polynomial if and only if this pk is a non-negative log concave sequence which has no internal zeros. So sequence being log concave means that pk squared is at least pk minus 1 times pk plus 1 for all k. But let me point out that there is a small but non-trivial combinatorial condition appearing in this solution to the realization problem, that of no internal zeros. So this condition means that in the sequence, if you have 2 non-zeros, it's somewhere in the sequence, every number in between the 2 non-zero numbers should be non-zero as well. And this is not implied by log concavity. For example, 1, 0, 0, 1, 2, 2 is a log concave sequence of non-negative numbers, but it has clearly internal zeros. So that is Sheffard's solution to d equals any and n equals 2 case. Regarding the extension of Minkowski's necessary condition, Alexander van Venkel in 1930s made the following fundamental observation, which now goes by the name of Alexander Venkel inequality. One way to state is that for any collection of convex bodies C, and for any choice of non-negative vectors V1 to Vd in Rn, if I take the directional partial derivatives of the volume polynomial of C, denoted Fc here, in directions V1, V1, V3, Vd, and I take the directional derivative with respect to V2, V2, V3, Vd, then that is bounded above by the square of the directional derivative of V1, V2, V3, Vd of a f of a C. So remember that this volume polynomial Fc is homogeneous of degree d. So if I take partial derivatives d times, it becomes a single number. So the inequality that you're looking at is the inequality between two numbers given Vi. But the assertion is that this inequality is true for every choice of non-negative vectors Vi. So it's some complicated statement with quantifiers. But for each Vi, it's an equality between numbers. Okay, so I'm going to return to Alexander Fenkel's result. This is a very deep result, proved with very interesting methods. But now let me try to change the setup a little bit and discuss the realization problem for volume polynomials in the setting of linear algebra this time. So here, instead of convex bodies, I'm going to look at sequence of d by d positive semi-definite matrices. This will be A1 to AN, and there will be corresponding variables x1 to xn, and the partials, partial 1 to partial n. And I'll say that the volume polynomial of such a collection A is given by the determinant of the linear combination of AI with coefficient xi. In this case, it's even more clear than the previous case that this volume polynomial is a degree d homogeneous polynomial in n variables xi. And it is also very, very believable that this polynomial will only have non-negative coefficients because all the AI are PSD. And these coefficients are called mixed discriminants, also studied by Alexandrov, related to his work on Alexandrov-Fenkel inequality. And in this setup, realization problem for volume polynomials of PSD matrices is again to describe the set of all degree d volume polynomials in n variables. In other words, the task is to find all inequalities satisfied by mixed discriminants of n d by d matrices. So of course, this is a very classical topic, finding all the determinantal inequalities between some set of PSD matrices. And the classical conjecture of Lax, Peter Lax, gives the complete answer when n is at most 3. So this is a theorems of Luis Perillo, Ramana, and Helton and Vinnikov, which says, for example, that if you are in the situation where you're looking at 2 by 2 matrices and 3 of them, then the corresponding polynomial, a quadratic form in 3 variables, is a volume polynomial of PSD matrices if and only if Pij is a Lorentzian matrix. So it's very, very similar to Rudolf Heine's result on convex bodies. On the other hand, in the case when D is anything but N is 2, the solution to the realization problem diverges from convex body case to PSD matrix case. Because here, fx1, x2 is a volume polynomial of 2 PSD matrices if and only if the polynomial is real rooted in the precise sense. So this implies the log concavity condition appeared in Shepard's characterization, but not conversely. And the same observation that Shepard made can be also made in this setup, namely that the elementary symmetric polynomial in 4 variables is not a volume polynomial of 4 real 2x2 PSD matrices, simply because the dimension of the space of 2x2 symmetric matrices is 3, which is less than 4. So it forces a kernel to appear. Alexandrov proved the same kind of inequality in this linear algebra setup. And the statement is basically the same, just replace convex bodies with PSD matrices everywhere and replace volume by determinant everywhere. And again, in general, we still do not know a complete characterization of volume polynomials of PSD matrices. The last setup I want to put it in parallel is that of algebraic geometry. So this requires a little bit of more background, but not too much. So let's say we are working over a field when we look at the d-dimensional projective variety over K. This is a solution set of some polynomial system of equations. And here, our input will be sequence D, 1 to Dn, where each di is a so-called base point free divisor on Y. This means that di is the pullback of a hyperplane under some map from Y to projective space. And the volume polynomial of the sequence D is given by taking the top self-intersection of the variable linear combination of the di's, where the product is taken inside the cohomology ring of Y. So if you know about cohomology ring and the fact that it is a ring so that you can multiply in it, it's again pretty clear that this function in question is a homogeneous polynomial of degree d in n variables. What is a little bit new compared to the previous situation is that the polynomials you get in this way always have non-negative integral coefficients, because you are computing inside the cohomology ring with integer coefficients. So it can only produce integers and not some random real numbers. So this forces us to distinguish between many different types of realization problems. For example, I can ask realization problem up to a rational multiple and say that f is in the set VDN-QK if up to a rational multiple f is equal to fd for some collection d on y over k. And I can also ask the realization problem up to taking limit and say that the set VDN-RK is a limit of polynomials in VDN-QK. These are the realization problems with Q coefficients and R coefficients. This is a rather elaborate setup, but the beauty of it is that it subsumes many of the realization problems that we discussed so far. So there is this very well-studied class of algebraic varieties called toric varieties, and the theory tells you the following. So if you have a collection of convex bodies, each of which is a rational polytope, so it's a polytope, all of whose vertices are rational, then the corresponding convex body volume polynomial is in the set VDN QK for any k. This is the nature of the construction of a toric variety from the corresponding polytope. And one conclusion that you can make out of this is that in general, when C is just some collection of arbitrary convex bodies, then its volume polynomial is in VDN RK for any k, simply because you can approximate any convex body with a rational polytope. Okay, and the second setup that I want to mention is this another classical class of abelian varieties. And the theory of abelian varieties, which is very, very well developed, has the following property. So if you have sequence of d by d rational PSD matrices, then actually you can find the corresponding divisor on an abelian variety with the property that the top self-intersection is the determinant of the PSD matrix that you use to construct the divisor. So the conclusion is that FA, formulated in terms of linear algebra, is actually in the set VDN QK for any k, and therefore, in general, the linear algebra volume polynomial will lie in the set VDN RK for any k, because any PSD matrix will be a limit of PSD matrices with rational entries. Okay, and then in algebraic geometry, the realization problem for volume polynomials is simply to give an explicit description of the set of all volume polynomials and their limits. So to describe the set VDN RK. So this is the same as asking for finding all the inequalities satisfied by intersection numbers of n base point free divisors on a d-dimensional projective variety over k. And what I think is a much harder problem is to describe the set VDN QK. So this is the same problem before and after taking the closure or taking the limits. So remember the fundamental inequality that Alexandrov and Fenkel found around 1930s. And unknown to them, I'm not entirely sure, but probably, Hodge was working on his theory of harmonic forms and noticed that out of this theory, the inequality that looks identical to the conclusion of Alexander Fenkel of convex bodies just shows up. Maybe he did not know. The statement is that for any f in VDN RK, so volume polynomial in the sense of algebraic geometry, the conclusion of Alexander-Fenkel theorem is still true. So that's 1930s, and like many important discoveries, they were discovered simultaneously, more or less. And then it took mathematicians many years to realize that the two discoveries, one in convex geometry and another in algebraic geometry, are actually the same statements in the following sense. So you can use Hodge's theorem to prove Alexander-Fenkel. This is work of Khovansky-Tessier in the 70s. And conversely, Hodge's inequality can be deduced from Alexander-Fenkel. This is the work of Kave, Khovansky, and Lazarsfeld-Mustata. So many different fields meet at this common intersection. So for what values of d and n can we understand the set of all volume polynomials over field K in the sense of algebraic geometry? Some of these characterizations can be deduced from the corresponding statement for convex bodies. So for example, when n is equal to 2 and d is anything, this Shepard theorem tells you that f is in VD2 RK if and only if the coefficients Pm form a non-negative log concave sequence with no internal zeros. simply because you can use the theory of toric varieties to turn the convex bodies into toric varieties. So one of the new contributions, a small contribution, but still a new case regarding the realizability, is a case when d is equal to 2, but n could be arbitrary. So in this case, I have an n variable quadratic form f, and the question is, up to taking limits, when such a thing is a limit volume polynomials of projective varieties over K. And the statement is that for any K, F is a volume polynomial if and only if its Hessian Pij is a Lorentzian matrix. So at most one positive eigenvalue. Okay, now I want to emphasize a small thing that is becoming more and more apparent, but I did not emphasize yet. So algebraic geometry, one of the beauty of it is that you can do it over any chosen field, K. You can do complex algebraic geometry by taking K equals C, but you can also do very interesting algebraic geometry over finite fields and so on. And on all the statements that you have seen regarding volume polynomials in the sense of algebraic geometry, the characterization of the set VDN did not depend on K. This is a very subtle statement. Well, that's the conjecture that I'm proposing. And if this is true, it must be a very subtle statement because before taking the closure, so if I take the set VDN QK, these are the literal sets of volume polynomials before taking limits of them. This set does depend on K. So for example, if you look at the picture of this famous Fano plane F7, this configuration of 7 points and 7 lines in characteristic 2. And if you look at the so-called basis generating polynomial, which is degree 3 polynomial in 7 variables, where I have a monomial x1, x2, x3 if 1, 2, 3 are in general position in the Fano plane, and so on. So that in total, I have a 28 monomial terms. And after some work, you can show that this F belongs to V of a 3, 7 with a QK if and only if characteristic of K is equal to 2. So the content of conjecture 1 is that after taking limit, VD and RK do not depend on K. Okay, that's already, I think, is a pretty bold conjecture in algebraic geometry. But I want to propose something even more stronger that sort of would explain why the independence on the field might be true. So in another joint work with my collaborators, we developed this theory of minors for polynomials and polymatroids. And this is supposed to be extension of the theory of minors in graph theory and matroid theory. So instead of writing down the definition in full, let me just point out that if I write my polynomial f as a descending order in the degree of the variable xn, and then each one of the polynomials in one less variable that appears as a coefficient in such an expression, fm, will be called a minor of f. And using this terminology, what's odd about the class of volume polynomials, convex bodies, and PSD matrices is that they are not closed undertaking minors. So for example, we discussed the fact that there are no 4 equiangular lines in R2. But clearly, there are 4 equiangular lines in R3. So I can take this, 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 this. So put a tripod and put one stick on side. This is equiangular line of 4 inside R3. And if you compute the volume polynomial of this collection, you see that the elementary symmetric polynomial of degree 2 in 4 variables appearing as a minor of the volume polynomial. This shows that the class of volume polynomials of convex bodies is not minor closed. On the other hand, the volume polynomials in the sense of algebraic geometry, which encompasses volume polynomials in the sense of convex geometry and positive semi-definite matrices, is closed under taking minors. So with my collaborator Shuda Wang, we were led to inspect the insane sounding possibility that perhaps the class VD and RK do not depend on the field K because it is a limit of minors of volume polynomials of convex bodies. So if this is true, then independence on K will be automatic. So this sounds like a complicated statement, but in fact, it has a very, very concrete interpretation that lets you disprove easily in case it is not true for some particular values of DNN. It says that every valid inequality for mixed volumes of convex body must have an algebraic geometric analog. That's what it means. So if you want to disprove conjecture 2, all you have to do is pretty straightforward. Do a thorough literature search by yourself or letting your ChatGPT do it for you. List all the known inequalities that involve mixed volumes of convex bodies and choose your favorite one and show that that particular one cannot be deduced from algebraic geometric technique. More precisely, you show that there is no corresponding algebraic geometric inequality by finding a projective variety with divisors on it that violates your inequality. That would disprove conjecture 2. And the content of a conjecture 2 is, of course, that you cannot do that actually. Every valid inequality has algebraic geometric source. So in the concluding part of my talk, I want to go combinatorics. And there is a combinatorial analog of all the statements that I have been discussing so far. And amazingly, this was also developed around the same time without knowing anything, I suppose, about the relevant works of Podge and Alexandrov and Fenkel. This is a work of Whitney, Hessler-Whitney, on matroids. So this definition was that the rank D matroid on N is a collection of D-element subsets of N satisfying the symmetric exchange property. So you may have seen this property in your linear algebra course when you're trying to show that any two bases of a finite dimensional vector space have the same cardinality. So for any B1, B2 in J, and any I1 in B1 not in B2, there is I2 in B2 not in B1, such that exchanging I1 and I2 from B1 and B2 produces a new pair of bases. So later, Gelfand, Goreski, McPherson, Serganova in the 80s found that equivalently, you can define a matroid by saying that all the edges of the convex hull of basis indicator vector EB in Rn have directions EI minus EJ. And of course, concerning matroids, this realizability problem is a very, very old one. So the situation is that if you have a configuration of vectors or hyperplane arrangements defined over a particular field K, it defines a matroid that is realizable over that field. And the point is that not every matroid is realizable over every field. So this gives you a hierarchy of matroids according to their realizability. So graphic matroids on the very bottom, and then graphic matroid will be regular matroid, meaning that it's realizable over every field. And regular matroids are linear matroids over K, and that's included in the class of algebraic matroids over K. And that's included in the class of all matroids. And you can show by example that every single one of the inclusions shown here is a proper inclusion. So Fano, non-Fano, non-Desargues, and so on. And the realization problem for matroids asks for an explicit description of these classes. Okay. So what's this matroid thing has to do with volume polynomials? So what I proved with my collaborator Peter Brandon in KTH is the following. So if I have a volume polynomial, so element of VD and RK, then the support of this F, which is a set of all monomials appearing with non-zero coefficient in F, must form the basis of a matroid. So this will be literally a matroid if my polynomial only has square-free monomials, but in the general case, what I get is a polymatroid. And another thing that I prove with my group of collaborators, Brun, Mialek, Sus, and Wang, is that you sort of have this converse characterization, which says a polymatroid or matroid is the support of some volume polynomial with Q coefficients over field K, if and only if it is an algebraic matroid over K. So here algebraic means that it's realizable by algebraic independence in the sense of field extensions. That leads me to another very bold conjecture, which roughly says that every matroid or every polymatroid is realizable, in fact, by the volume polynomial in algebraic geometry over a field. This, if you have some experience with theory of matroids, should be interpreted as a very surprising statement, because if you take the traditional known of realizability in the sense of matroid theory, you know that almost all the matroids are not realizable over any field. There, the point is that in VD and RK, I not only take volume polynomials of projective varieties, but also put in limits of them. So that is roughly what I wanted to share today. So let me give you an executive summary of what roughly happened very quickly during the last rough 50 minutes. So there is this class of volume polynomial, but in fact, there is not a single class of volume polynomials. Many different mathematicians working on very different fields simultaneously or in some different order have arrived at this notion of volume polynomials in convex geometry, in PSD linear algebra, and also in algebraic geometry, and to some extent in some part of combinatorics. And they are intimately related. They tend to satisfy the same kind of inequalities. And one of the ambitious conjectures that are proposed here was that Well, some of those classes are minor closed, some others are not minor closed. But if you take a minor closure under minor relationship, the prediction is that they define more or less the same class of polynomials, meaning that they satisfy exactly the same class of inequalities. Inequalities of the kind Alexander Fenkel or Hodge or the one discovered by Riemann, and probably many more waiting to be discovered. But there should be a very tight connection between these various volume polynomials regarding different types of objects. And as a byproduct of this philosophy, which may be a nonsense, remember all this is just conjectural, I did not prove anything, is this possibility that every matroid is in some generalized sense realizable over every field. And in some generalized sense here means in the sense of the theory of volume polynomials. So the original inventors of the theory of matroids have been puzzled by the existence of this many non-realizable combinatorial configurations or matroids. And they were worried about the possibility that they might be missing an axiom to put in to exclude these non-realizable matroids as a valid combinatorial object. And many have been looking for this missing axiom of matroid theory for many years, and none found it. And there are some sort of logical reasons why there are no missing axioms. So perhaps what was happening is to just include the limits of volume polynomials when considering the realizability problem in this level of generality. So that is what led to conjecture 3. Okay, so that's I guess my talk today, and I'll be happy to answer any questions you might have.
Thank you very much, Professor Jung Ha, for this beautiful and inspiring lecture. We truly appreciate you taking the time to share your insights with us today. We now have some time for questions. You can unmute yourselves and raise your hand if you have a question. Maybe in the meantime, I can ask you something.
Yeah.
Thank you. You mentioned in the first slides from Heine's observation.
Okay,
This
let me go
case-
there.
Yeah.
Yes, there's Minkowski and here's Heine.
Yes. You mentioned that. Could you say a few words about what makes the problem in this case for not having this? Sorry.
Yeah. So why is this still unsolved?
Unsolved. Yeah. Yes. Sorry, I could.
I don't know. I also find the situation very ridiculous. But sometimes, like innocuous looking problems in maths can be secretly very difficult, or maybe not. Or
Okay.
you can ask your ChatGPT to see what it thinks.
Okay.
But certainly, certainly many people in the 30s have tried.
Yeah.
Well, and now we know much more mathematics, I'm sure. So there are plenty of things that we can also try. But this is a very time-consuming business. So what you have to solve this case is that you have to write down what you think is a complete list of valid inequalities for mixed volumes in the plane of 4 convex bodies. So that's the guessing part. And assuming that you did that part correctly, you have to do the very tricky construction problem, which is that if somebody gives you just bunch of numbers satisfying all your inequalities, And your job is to find 4 convex bodies with exactly given numbers as mixed areas or mixed volumes. And this can be often very, very tricky.
Okay. Okay.
And the second part will be complete waste of time if the first part of your guesswork is not the correct one. So it's very easy to spend infinite amount of time trying to do this. And maybe that's the reason why this simple looking question has not been solved yet.
Okay, so it's a lifetime problem.
Or it could be done in a 1 hour if you're lucky. It could be, you never know which way it will go.
Okay. Okay. Thank you very much. Yes, I have some raised hand from Duan Cardona. You can unmute yourself.
Okay, Professor Ho, thank you very much for your very nice talk. Sorry, I am not from the field of combinatorics, but I have a question that maybe doesn't make sense, but I will try. It was about one inequality that you show at the very beginning in your talk about some vector
Okay.
fields and a sum, right? You had something like D vector fields and later
Oh,
an
I see.
inequality, right?
Yes. Let me go there. Here.
Uh-huh. Right. Yeah, exactly. You mentioned this inequality. My question comes from the fact that you are using here D vector fields, but n is the dimension, right? Is some relation between D and n here or not necessarily?
Yes, so D and N are given numbers. I am looking at n convex bodies, each of which has dimension D.
Okay, okay.
So that gives me a volume polynomial that has degree D.
Okay.
So if I differentiate D times, I get a number.
Now I
And
understand. Okay.
in this inequality is that of numbers.
Thank you very much. Thank you very much.
Thank you. Now we have a question from Pedro Fernandez. Pedro, you can unmute.
Thank you, Professor Ha, for your very nice talk. I just have a curiosity, maybe in your example of 4 bodies in the plane. I just
Yes.
noticed that the sum of the eigenvalues are is like 0. I think it's just something casual, or is there any structural reason behind that?
Yeah, so if you look at this matrix, you can see that the diagonal entries are all 0, which makes the trace 0, which makes the sum of eigenvalues 0, I guess. And the diagonal entries will be the coefficients of the square terms in the quadratic form, and there are none, which means that we are looking at convex bodies, each of which has area 0. So mixed
Okay.
areas can be non-zero, but each one of the which has a area equal to 0. That's how Heine knew that this thing is not a volume polynomial. Because area 0 means that you're looking at line segments, but if you have 4 line segments, not all of the remaining mixed coefficients can be equal to each other because there should be different angles between some of those 4 lines.
Okay, thank you. Thank you, Professor.
I think we have just one last question and a comment. So, given a volume polynomial, can one recover the PSD matrices or convex bodies that produce it? Is such a reconstruction useful? And if so, are they unique up to some equivalence relation?
So this is also related to the fascinating subject in algebraic geometry. But let me first try to answer the question in the setup it was posed. So the answer, blunt answer would be no. So many different set of convex bodies will produce the same volume polynomial. And this is roughly upgraded version of the trivial statement that there are so many different convex bodies having the same volume. And in general, the set of all collections of convex bodies producing the same volume polynomial will be huge. And what is interesting about this formulation is that it has a clear analog in algebraic geometry, which turns out to be also a very, very classical problem. This is the question about describing the moduli spaces. So if you have a variety, and if you have some subvariety, then it has a homology class. And then the question arises, if you fix a homology class, what can you say about the set of all subvarieties having that homology class as its homology class? And this is the beginning of the theory of moduli spaces. For example, if you do this with linear subspaces, you get the moduli space of linear subspaces, which is Grassmannian's, the most famous moduli space. But you can do this with not just degree 1 subvarieties, you can do it with degree 2 subvarieties and so on. Then you get more and more complicated moduli spaces of subvarieties. And these goes under the name of Chow varieties. And algebraic geometers had a lot of fun in wasting time to understand some of this extremely complicated nature of these moduli spaces. And I do not know much in the setting of PSD matrices and convex bodies, but the general expectation is that these questions tend to be very difficult. So I have posed many realizability problems, but this question that was just asked is the finer question about the geometry of realization spaces. And there are many instances where this realization space question tend to be impossibly difficult. And sometimes people even makes precise what it means to be impossibly difficult. So you might want to Google things like Minev's universality theorem and its cousins, which shows that it could be as difficult as any problem that you can pose in the given first order language of whatever setting you are in.
Okay, Professor. If there are no further questions, let us once again thank Professor Jung-ha for his outstanding lecture. And on behalf of the organizing committee, Professor Jung-ha, thank you very much for being with us today. It has been a great honor and a privilege to host you at ICMAM 2026.
Yeah,
Thank you
very much, and thanks for listening. Yeah, it's been fun.
Thank you very much. We will continue with the talk of Professor Pierre Shapira. We will be Brian, are you here?
Yeah, I'm here. Can you hear me?
Hello, Professor Pierre. How are you?
Okay, so I have my slides. Yeah. What shall I do with my slides? Okay. Je te le faire en fait.
Just give us a moment. We will.
Okay. I'm here. Sorry.
Yeah. Okay.
Thank you, Andrea.
Un écran?
Thank you. See you.
1 second. Okay. Okay, can you see me on see the slides?
Yes. Yes, Professor Shapira.
Okay.
We can see your slides now.
So
thank you, Professor, for being here. Maybe I can say some words to introduce your talk. It is a pleasure for me to introduce our next speaker, Professor Pierre Shapira. He's an emeritus professor at Sorbonne University. He's known for his important contributions to algebraic and microlocal analysis, shift theory, and the modules. In 2023, he received the Sophie Germain Prize from the French Academy of Sciences in recognition for his contributions to fundamental mathematics. We're very pleased to have him with us today, Professor Shapira. Thank you for accepting our invitation and thank you for joining us today. It is a great honor to have you here. Please go ahead.
Okay, thank you. So thank you to the organizers. The honor is for me. I'm very happy and proud to speak at this opportunity of this important meeting. But my talk will be very conceptual, not so many technical details. The subject is space-times, for well known from physicists on general relativity, but from the point of view of sheaves on mainly macrolocal sheaves theory. So, in fact, what I want, my aim is essentially to show, let me look at the time. Yeah, my aim is to show that macrolocal sheaves theory makes things relatively easy, much easier than the classical infinity or distribution point of view of most of the analysts on hyperfunctions replacing distribution. The aim is to solve globally the Cauchy problem for hyperbolic D modules. So some short introduction. A space-time classically is a connected manifold with a non-degenerate quadratic form of signature plus, minus, minus, etc., minus, like the term model is a Minkowski space. Classically, when you have such a manifold, sometimes I call it a causal manifold, one problem is to define the future of a point, the light cone. Usually, classically, you do that by using causal curves, but I will do it by a totally different method. Associated to the quadratic form, there are various wave operators, the Lambertian, and it's natural to try to solve the Cauchy problem globally in the space of distribution or infinity function with an equation associated to this form. But here we will treat not only one equation but general system, that is D modules, and we will work in the space of Sato's hyperfunction. Okay, the classical literature on this subject is huge, about globally hyperbolic spacetimes and the Cauchy problem in the framework of distribution. We can quote the names of Brunetti, Fredenhagen, Baer, Ginoux, Pfeffler, Bernal, Fati, Siconolfi, Geror, Hawkins, Minguzzi, Sanchez, and in fact many others. But I will have another way to treat the problem. We will work with Sato's hyperfunction on macrolocal sheaves theory. So the Cauchy problem has also a very long and classical history. Maybe it starts with Cauchy-Kolevsky, which are not written on this slide, but of course they are the first one on their theorem, as we shall see, is still the only one which is useful, in fact. But there are many names, like Adama, who first show that if you take the very simple operator dt square minus dx on R2, and you look at the Cauchy problem with data and t equals 0, then it is not well posed in infinity or distribution framework. There are very difficult work by Hermander classifying hyperbolic differential operators with constant coefficient, but to say the truth, it's not very useful. And with variable coefficient, very little is known in the classical setting, except for operators which are called with simple characteristics, that is, operators which are macrolocally equivalent to the partial derivative with t. Okay? But with hyperfunction, the Sato's hyperfunction, the situation is radically different. For example, with Bonney in 73, we showed that we can solve the local Cauchy problem for what was called at this time weakly hyperbolic operators, that is, operators whose principal symbol is hyperbolic. Okay. And with Kashiwara, we have extended this result to general systems. General system of partial differential equations means D modules, and we will come back to this. I will explain more precisely. And with Benoit Jubin, we have proved a global, we have solved a global Cauchy problem with the help of what is called a Cauchy time function that I will describe later. Okay. Okay, so the plan of my talk, maybe I will not read everything, but let's say that section 2 to 4 are joint work with Kashiwara. 5 to 7 is a joint work with Benoit Jubin. And 8 about the Big Bang. So for those who are interested in it, I will give a purely mathematical interpretation of the Big Bang. A Big Bang view as a Hamiltonian isotopy. And this purely mathematical Big Bang is adapted from work with Guillermo and Kashiwara. Okay, so first I give a shift theory on the 6 Grothendieck operations on one slide. Okay, maybe it's not enough, but I cannot make a course on shift theory. So a pre-shift, as I hope everyone knows, I work on a field, I work with pre-shifts of vector spaces. So a pre-shift, M is a locally compact space, and in practice it will be a C-infinity manifold, in fact. So, or sometimes a complex manifold. So a pre-shift F on M is a contravariant functor from the category of open sets to the category of K vector spaces. So to each open set U, we associate a vector space F of U, and if U is contained in V, we have a restriction map which goes from F of V to F of U, exactly as you have the restriction of the infinity function or restriction of distribution or any functional space that you are familiar with, you can restrict functions. So that's a pre-shift. And a pre-shift is a shift if you can glue things. More precisely, if you have a section which is locally zero, then it's globally zero. It looks obvious, but it's not always obvious. If your shift is a shift of co-kernel of a differential operator, locally maybe you can solve your equation, but globally you cannot solve it. So a section which is locally zero is globally zero. And if you have a family of sections on an open covering, and if the sections are compatible, if they glue an intersection 2 by 2 of the covering, then they define a global section. And we work in the derived category. So of course I will not give a course on derived category, but what you should remember is that instead of taking one object, a sheaf of infinity function, for example, or the sheaf of locally constant function, we look at complexes, complex of objects. So, for example, the de Rham complex, in the derived category, the de Rham complex is isomorphic, it's the same thing in some sense, as the sheaf of locally constant function. And similarly, on a complex manifold, the Dolbeault complex is isomorphic to the sheaf of holomorphic functions. Okay? And we have the 6 Grothendieck operations. That's for the specialists. For people who are not used to shift theory, I think it's out of the scope. We have the tensor product, the internal Ohm, derived are Ohm. And when we have a morphism of manifold or topological space from M to N, we have 2 inverse images and 2 direct images, one with proper support, the other one without condition. Okay. Now I will have a macrolocal point of view on this question. So macrolocal analysis was created by Mikio Sato in the 70s, giving rise to a very important paper, very influential paper. I'm not sure many people read this paper, but it was after rewritten by Hermander in the Sinfinity context, a paper by Sato, Kawai, Kashiwara in 73. And later in 82, with Kashiwara, we adapt the idea of Sato of being macrolocal, and we define macrolocal sheaf theory based on the notion of macro support of sheaves. So what is the idea? You have a manifold M on a sheaf that is an object of the derived category. Then the macro support is a closed subset of the cotangent bundle recording in which codirection the sheaf does not propagate. Okay, so the macro support, for those who are familiar with the distribution on a wavefront set, the macro support has connection with the wavefront set of distributions, but it's different, very different in fact, and it has connection with the characteristic variety of D modules, as we shall see very soon. So now I will be more precise. M is a Sinfinity manifold, and you have the cotangent bundle T star M, which project to M, on the sheaf on N. So the macro support is a closed set, so I describe the complementary. An open set W of the cotangent bundle does not intersect the macro support if for any point x0 of M on any real C1 function phi with whose conormal belongs to the derivative of phi, which is a covector belongs to W, then there are no sections of F supported by the half space defined by phi. Okay, phi of x bigger or equal to phi of x0. I will show a picture very soon. Okay, so P does not belong to the macro support of F if there is no local cohomology supported by the half spaces associated to the conormal P. Okay, so here you have an open set U with smooth boundary at x0 with conormal x0 psi 0. And if x0 psi 0 does not belong to the macro support of F, then the section, all cohomology group of F defined on U will extend through the boundary to a bigger open set. Okay, so I will give examples. So if A is locally closed, and if Ka is a constant sheaf on A, with 0 on M minus A, extended by 0, then we can define the conormal bundle to A as the macro support of the constant sheaf on A. For example, if N is a closed submanifold of M, the macro support of the constant sheaf on N is the conormal bundle, the classical conormal bundle. But you can generalize this definition to any locally closed subset. And in particular, if you take A equal M, if F is a non-zero local system, that is a locally constant sheaf on M, then the macro support of F is the zero section. The zero section is written as a conormal to itself, T star MM. That is the zero section of the cotangent bundle. In the complex case, I skip example 3 because I will come back to it in a few slides. Okay, there is a link between macro support and characteristic variety of D module. And let's look more precisely at the last example. I take the simplest case. M is R. Okay, so we can represent T star M as R2. So if I take the constant sheaf on the interval I, the macro support can be very different according if I is open, half open, or closed. Here on the left, you have the case of half open interval, and on the right, closed interval. And you can see, but that's for the specialist, that on the left, the macro support is up to homotopy, disjoint from the zero section. And it's related to the fact that the Euler characteristic of the half-closed interval is 0. On the contrary, on the right, up to homotopy, the macro support and the zero section always intersect. So, yeah, I forgot one slide. The macro support is conic for the R plus action. Its intersection with the zero section is the support of F. We have the triangular inequality, which says that if you have an exact sequence, or in the language of derived category, if you have a distinguished triangle, F1 to F2 to F3, then the macro support of any of the sheaf, F, is contained in the union of the two other, of the macro support of the two other sheaves. And a very important property is that the macro support is co-isotropic. One also says involutive. So I don't want to be more precise on this subject, which is very difficult, because the macro support is a closed set, but it's not a smooth manifold. So to be co-isotropic, we need to use the Whitney normal cone. But if the macro support is smooth, then at P, in a neighborhood of P, then to say it's co-isotropic means, as usual, that the tangent space at this smooth manifold contains its symplectic orthogonal. In particular, the macro support cannot be too small, because when it's smooth, the dimension of the macro support is at least the dimension of M, of the base manifold. Okay? So I've given example, and now I have a glance to the functorial properties of the macro support. Mais tu crois qu'on va, non? C'est pas gênant. So when you have a real manifold, you can associate its tangent bundle on its cotangent bundle. Okay. If you have a submanifold, you can associate the normal bundle on the conormal bundle that we already met on the zero section T star MM. Now, if I have a morphism of a real manifold, that is a map, it's infinity map, from M to N, if I take the tangent map, it goes in the good direction. It goes from Tm to Tn, and between them, I go to M over N Tn. Okay, I have this diagram of vector bundles. And if I take the dual bundle, the cotangent bundle, then the first map F prime go backwards because it's a transpose of this map. So in fact, we get a relation. No more, there are no cotangent map from T star M to T star N, but we have a relation with, in the middle, the product over N of M by T star N. Okay? And this diagram on the right is a basic diagram of macro-local analysis. I guess that those who have encountered a wavefront set of distribution already have seen such a diagram, maybe with different notation. Okay. Okay, and there is the notion of being non-characteristic. So if lambda is a closed conic subset of T star N, one says that the map F is non-characteristic for lambda if the inverse image of lambda by F pi does not intersect the inverse image of the zero section by Fd outside of the zero section. Maybe I go backward. You have this diagram, Fd from M cross T star N to T star M on F pi, and non-characteristic means this. For some manifold, it's exactly the same thing as transversality. if lambda is a conormal bundle to a submanifold, it will say that F is transversal to this submanifold. So we have a basic theorem now. First, I start with a sheaf on M, and I assume that F is proper on the support of F, a natural condition when you integrate. Okay. Then the macro support of the direct image of F is contained where you expect it. What can you do with the macro support of F? You take the inverse image by Fd on the direct image by F pi. And similarly, if you have a sheaf G on N, and F is non-characteristic for the macro support of G, then the macro support of the inverse image is contained where you expect it in F pi minus 1, in the direct image by Fd of F pi minus 1 of the macro support of G. And moreover, in the non-characteristic case, the two inverse images are isomorphic up to a shift on an orientation. Omega Mn is a relative dualizing complex. It's for specialists. But it's interesting. Usually in algebraic geometry, people look at morphisms which are smooth. And of course, if F is smooth, it's non-characteristic for any lambda. I should have said it. Okay? So it's a generalization of being smooth. It's smooth with respect to lambda. Okay? And in this case, the two inverse images are isomorphic. So I want to explain the link with D modules. So again, D modules in one slide. So now we have a complex manifold with a structure sheaf OX, and we also have the sheaf DX of finite order holomorphic differential operators on X. I have not written it, but a section of DX is a polynomial with respect to the partial derivative and with coefficient holomorphic functions. So a coherent D module is a mathematical way. In fact, when you have a ring or a sheaf of rings, a coherent module over this ring is the algebraic way to speak of linear system of equation over this ring. Okay, so for D module, it's a mathematical translation of a system of linear partial differential equations, but not square matrices, general matrices, general system. So locally, M, the D module M, admits a finite free resolution, which is not unique, of course, depending on the generator you have chosen on M, but you can locally write M, extend M by a long exact sequence, which stop. It's a difficult theorem of D module theory. It does not go to infinity. It stops. On here, the Pn minus 1, etc., and so on, P0, are matrices of differential operators acting on the right. So if they act on the right, the co-kernel is a left D module, okay? Because D, of course, is not commutative. Okay, and if you look at the complex of its holomorphic solution, denoted R-OM-MOX, this is the complex obtained by applying the contravariant functor OM with value in OX, and we find this complex, which in general is not exact at all. Okay, for example, if M is associated to one equation with one unknown, that is M is dx quotient by dx times p, where p is a differential operator, then the complex of its holomorphic solution is nothing but p acting on the left on OX. Okay, so the complex R-OM-MOX contains the information of the kernel of p and the co-kernel of p. In this language of derived category, we make no difference between kernel and co-kernel. So when you have a coherent D module, you can associate its characteristic variety in the cotangent bundle, T star X, and it's a closed conic analytic variety. if M is associated to one differential operator, then the characteristic variety is given by the zeros of the principal symbol of P as usual. Okay. On the important theorem by Sato, Kawai, Kashiwara assert that the characteristic variety of a coherent D-module is co-isotropic, or if you prefer, involutive. But now the characteristic variety is a complex analytic variety. So to be co-isotropic simply means that at the generic point of this variety, which are smooth, then it's a co-isotropic submanifold. Okay. And later, Olaf Gaber in 1981 gave a purely algebraic proof of this very important theorem. And before Gaber, there were partial results by Guillemin, Quillen, Sternberg. Okay. So now I can state the Kashiwara, the Cauchy-Kalevsky or Cauchy-Kalevska-Kashiwara theorem. You have a morphism of complex manifold. You have a coherent D-module, M on X, and you can define the induced D-module. I don't do it here, it's a little technical. It means the D-module which will be satisfied by the inverse image of function. If you have function on X, you take the inverse image on Y. So if the function on X are solution of M, then the inverse image on Y will be solution of My. And one says that Y is non-characteristic for M if Y is or F is non-characteristic for the characteristic variety of M, the same definition as above. And then the classical Cauchy-Kalevsky theorem can be extended to general system of linear differential equation. Yeah, that's Kashiwara's master thesis in 70, which says that if F is non-characteristic, then the induced system is again coherent, and moreover, the inverse image of the sheaf of holomorphic solution of M is isomorphic to the sheaf on Y of holomorphic function on Y of the induced system My. But there is another application of Cauchy-Kalevsky that I will give now. That's the link between the macro support of the complex of holomorphic solution of M and the characteristic variety of M. In fact, there is a theorem that we have proved with Kashiwara long ago, which says that the macro support of the complex of holomorphic solution is equal to the characteristic variety of M. Okay? So on the proof, there are two inclusions to prove, but the most important is to prove that the left-hand side is contained in the right-hand side. And in fact, this proof is an purely algebraic consequence of the Cauchy-Kalevska theorem, but not the Cauchy-Kalevska as stated by Cauchy-Kalevska, but the refined Cauchy-Kalevska theorem as introduced by Petrovsky. I think Petrovsky was the first one to notice the importance of the precise Cauchy-Kalevsky theorem, which says that you can solve the Cauchy problem with an angle, in some sense. And this fact was used by Leray and explicitly formulated by Zerner. And for those who want a more precise statement, you can look at the first book of Hermander. I forget the name of the book. Hermander wrote 4 books on PDE. On the first book, last chapter, is concerned with analytic PDE, and he explained Zerner's theorem. Okay. And the other inclusion is more sophisticated and use the sheaf of macro-local operators of Sato, Kawa, Kashiwara. So this now we know by Sato, Kawa, Kashiwara that the characteristic variety of M is co-isotropic, involutive, and we know by the result with Kashiwara that the macro support of F is co-isotropic. So we have two very different proofs of the same result. One almost topological by the macro support, and the other one now almost purely algebraic by Gaber argument. Okay. Okay, so I need some part. This part is a little difficult, and I will be rather sketchy, because we need, for our purpose, to consider morphisms which are characteristic, and we need to give a bound to the macro support of the inverse image when f is characteristic. Then we need some symplectic geometry. So everything is real again. M is a real submanifold, closed submanifold of X. So we have the conormal bundle T star Mx, which project to M, and it gives rise to this diagram, the basic macrolocal diagram. And in taking the zero section of T star Mx, we find the embedding of T star M into T star Mx. This is an embedding because the projection here is submersive. And the cotangent bundle to the conormal bundle is isomorphic by the Hamiltonian isomorphism. It's a basic symplectic geometry. It is isomorphic to the normal bundle to T star Mx in T star X. Okay, so we can send T star M into this normal bundle. But we can also send the macro support the macro support of F. We can take the Whitney normal cone of the macro support. So it will be, I have not defined the Whitney normal cone, but it's a classical geometrical object. It means you take the cone which looks like as much as possible to the macro support. So if you take the Whitney normal cone along T star Mx, it's a closed subset of the normal bundle to T star Mx into T star X. So as above. So we are again in T star Mx, T star X. And we can define as a new macro support along M as the intersection of this Whitney normal cone with T star M. Okay. So it's very technical, it's a little difficult, very difficult, in fact, very technical. But there is a theorem which says that if we look at the macro support of the cohomology of F supported by M, it will be contained in this macro support of F along M. Okay, and I will use this result now. I will apply it to hyperfunctions. I look at my time. Okay. So now M is a real analytic manifold of dimension n, let's say, and X is a complexification. So on M, you have the sheaf of real analytic function, which is nothing but the sheaf of holomorphic function restricted to M. But you have another sheaf similar, which is Rm of the dual of the constant sheaf on M with value in OX. Okay, the dual of constant sheaf on M is Rm, Cm, Cx. And with the sheaf of Sato's hyperfunction is given by this Rm, and it's contained in concentrated in the single degree, and we find the cohomology supported by M of OX with the orientation sheaf of M. So roughly speaking, hyperfunction on M means cohomology supported by M of the sheaf of holomorphic function. Okay, so it's very natural. Okay, because when you have the sheaf of holomorphic function, you can restrict to M or take the cohomology supported by M, taking of course all cohomology group, because in degree 0 you find 0. Okay, so it's a nice sheaf, which is a flabby sheaf, and which much bigger and which contains distribution. So if I make similarly, if I have a coherent D module, I can define its characteristic variety along M, as I did for the macro support of sheaves. So it is T star M intersect the Whitney normal cone along T star Mx of the characteristic variety of M. And then combining the preceding result, the theorem that I give now is a corollary of the preceding theorem. If I take as a sheaf F the complex of hyperfunction solution of the coherent D-module M, then the macro support of F is contained in the what I call the hyperbolic characteristic variety of M, that is the characteristic variety of M along M. Okay. So, as a corollary, if I have a closed analytic submanifold of M, Y a complexification of N in X, and if I have a hyperbolic D-module M, which is hyperbolic with respect to the conormal bundle to N in M, that is a conormal to N in M hyperbolic with respect to M, then in this case, the Cauchy problem, local Cauchy problem, is well posed in the framework of hyperfunction. Okay. This is totally false with distribution. No? So now I want to globalize this result. Okay, that's where spacetimes appear. Okay, as I said, on a Lorentzian spacetime, you have the quadratic form, which gives a like cone. But here, for our purpose, we don't need any metric. We just remember of the cone, and we prefer to work in the cotangent bundle. So this part of the talk is a joint work with Benoît Jubin. So a causal manifold is a real manifold together with a closed convex proper cone, and I assume that the cone is never empty, that is, it contains the zero section. And the morphism of causal manifold means that a morphism of manifold such that the inverse image of the cone lambda n on n is the macrolocal inverse image is contained in lambda m. But if you prefer tangent map, the tangent map of the polar cone to lambda m is contained in the polar cone in lambda n. And in particular, R is a causal manifold because we look at the closed cone tau positive. So now that I have a cone, I can define what is a cone lambda. I can define what is a lambda set. A is a locally closed set, is lambda set, is the macro support of the constant sheaf on A is contained in lambda. And I will say that lambda is lambda open if lambda is open, and moreover is a lambda set. And similarly for being lambda closed. And then there is a proposition which is not difficult, which follows easily for the functorial properties of the macro support, which says that the family of lambda open sets define a topology. I will give examples very soon. And if I take the lambda closed set, I find the same topology, because if an open set is lambda open, if you take the complement, it will be lambda closed with the same lambda. The macro support of an open set is the macro support of the complementary outside the zero section. So we have to prove that it's stable by intersection and union. For example, for intersection, we use the fact that the constant sheaf on U1 intersect U2 is a tensor product of the constant sheaf on U1 and constant sheaf on U2. And the macro support of the tensor product is contained in the sum of the lambda, and lambda being convex, lambda plus lambda equal lambda. After there is some work, but it's not difficult. So we have a new topology, the lambda topology. So let's give the example of a finite dimensional real vector space. And you have a closed proper cone with non-empty interior, let's say, on an open convex set V. And take lambda as V cross the antipoda of the polar cone to theta. Okay? Then I have a causal manifold, very similar to the Minkowski space, of course. On the lambda topology, in this case, U is lambda open if U is U plus theta intersect V. Okay? It's not written on the slide, but on R, you can define a lambda topology. The lambda open set, if lambda is tau positive, then the lambda open set will be the interval minus infinity A, for A real, open interval from minus infinity to A. You can define a topology on R, and if you give a course on general topology, you can give this as an example. Okay, there are only this infinite interval. They are very natural, and it's a way to work macrolocally on R. So now we can define the future of A. I call it G plus lambda of A. It's nothing but the closure of A for the lambda topology, more precisely the opposite cone lambda A. Okay? So it defines a preorder which says that X is smaller than Y if Y belongs to the future of X, to the closure of X for this topology. So it's not the classical definition of the like cone. And the classical definition use piecewise smooth causal path, and you say that X is smaller than Y if you can find a causal path starting at X and ending at Y. Okay? So there are relations between this piecewise smooth order, PS order, and the lambda preorder, but I will concentrate on this preorder. But take care that Y can be in the future of X doesn't mean that X is in the future on the opposite cone, because there are some subtleties. Okay? And now I recall this is classical for people working in this field. What is a Cauchy time function on M? So you have M lambda. So a Cauchy time function is a submersive map from M to R, which is causal. And also, we have that Q, this time function, is proper on the future and on the past of any compact set. So if you have a compact set K, you take the like code issued from K, and you assume that the time function is positive, is proper on it. Okay? So G causal manifold is a causal manifold although with a Cauchy time function. And G here makes reference to Geror, who was the first one to introduce such time function. And note that if you have a time function, then it's increasing with respect to the lambda preorder. Okay, if X is smaller than Y for the lambda preorder, then Q of X is smaller than Q of Y. And with this preorder, the diamonds are compact. Diamonds is the future, future of a compact K intersect with the past of a compact K prime. So when you take the intersection, it's compact. And conversely, there are theorems by Geror, Bernard Sanchez, Fatih Sikonolfi, and others, which prove that when you have what is called a globally hyperbolic Lorentzian spacetime, then it admits a Cauchy time function. And to be globally hyperbolic means precisely that diamonds are compact, and also that there are no causal loop, but we don't need that, I think. Okay? So, a technical lemma, which is not difficult, but fundamental for what happened after. If I have a sheaf on a G causal manifold, and if the macro support of F does not intersect lambda, then when I take the direct image of F by the time function, I find a sheaf on R, and the macro support of this sheaf will be contained in tau negative. Okay? So if Q where proper on the support of F, it will be nothing but a consequence of the general theorem of the macro support of proper direct image, but here it's not proper, so it's a little more delicate. So there is a technical work that I done. It's written on the slide, but I don't bother you with this. And you take an exhaustive sequence of compact subset and take the future cone, and it will not change the macro support of F when you cut by this, and then it's proper and you can apply the theorem. So as a corollary, we have the following. You have a G causal manifold, that is a causal manifold with a time function Q, and you assume now that the macro support of F does not intersect the closed cone lambda as well as the opposite cone lambda antipodal. So they don't meet outside of the zero section. And I take a Cauchy hypersurface that is inverse image by Q of some point T0. Then this hypersurface will be non-characteristic for F. And the main result is that you can extend uniquely the section of F which are defined in the neighborhood of the hypersurface. They extend uniquely to the whole space. That is, the global section of F and M, on all its cohomology, of course, is isomorphic to the global section on the hypersurface N0 of F restricted to N0. Okay. So it's an immediate consequence of the lemma by taking the direct image of F and R. On R, the direct image will be a constant shift. So if I apply this to hyperbolic D module, then I can solve globally the Cauchy problem for hyperbolic D module when we're working with hyperfunction. More precisely, if I have a real, everything now is real analytic, including the time function. Okay, on X is a complexification of the real manifold M. I have a coherent D module M. I have a hypersurface N on its complexification Y in X. And I assume that the hyperbolic characteristic variety of M along M does not intersect lambda outside the zero section. And the characteristic variety of M is symmetric for the antipodal map, so I don't need to consider lambda antipodal. Then with this hyperbolicity assumption, then the global Cauchy problem for hyperfunction solution is well-polled for hyperbolic D module. Okay, we have this global result. Okay, so we cannot expect something better, but as we shall see, I wanted to give some example. Let's take a very simple example. We assume that M is n cross R, and Q is a projection on R. We denote by T tau the coordinates on T star R, and we take a differential operator of order at most 2 with principal symbol positive and not depending on tau. So there is no derivation in T in R. And I take dt squared minus R. Okay? Then this operator is hyperbolic in the sense of hyperfunction, of course. Huh? And we may apply the preceding result. Okay? So why is it hyperbolic? It's not so obvious, because if I take the principal symbol and I calculate it at xt square root of minus 1 eta, so x square root of minus eta is a local coordinate on T star mx, and I work on square root of minus 1 tau plus theta, then I find something which is not zero for theta non-zero. But if you want to apply the definition of being macro-local to be macro-hyperbolic, it's a little more subtle, more difficult, and you have to use the local Borner tube theory. So it's not obvious that this operator is macro-locally is hyperbolic in the sense of hyperfunction, but it is. Okay, it is hyperbolic, and so you can solve the Cauchy problem. So a particular case, which apply also for distribution now, if you take dt square minus the Laplace-Beltrami operator that you can multiply by some real analytic function, positive, plus lower order term. Okay? So it applies for hyperfunction, not for distribution, depending of if a of t is 0 and you have lower order term, it may not apply. Okay? So you can solve globally the Cauchy problem. So what is important is that when you work with hyperfunction, hyperbolicity depends only on the top order part. Okay? And we can solve globally the Cauchy problem. Okay? So for distribution, so we know what is a hyperbolic system of PDE, but I have no idea what means a hyperbolic system for distribution. Okay, that is, here it's weakly hyperbolic if you want. Okay, that is depending only on the principal symbol. If the lower order term appear, then there is no natural candidate for general system. Okay, and I recall Adama example, which shows that the very simple operator dt square minus dx is not, the Cauchy problem is not well posed for infinity function, but it is well posed for, and globally well posed for hyperfunction. Okay, but of course, if dt square minus r is hyperbolic, if r is elliptic. Okay. That's the case encountered by most of the analysts. Okay, so what about the Big Bang? So it's not to be taken too seriously, okay? But it's interesting, I hope. So look at the situation where you have a Cauchy time function q from m to r positive, a time function, on each nt, the inverse image of t, is a compact Riemannian manifold. So you can ask the question, what happens if the diameter of this compact Riemannian manifold goes to 0, when t goes to 0 by positive value? Okay, that's the Big Bang. Okay, so there are serious mathematicians like Riemannin and Mathilde Marcoli, and very serious physicists, Roger Penrose, who are interested in the Big Bang. Mathilde Marcoli from a mathematical point of view, and Penrose from a physical point of view. So here I will propose a purely mathematical candidate, totally different from that of Mathilde Marcoli. And in fact, it's a general candidate for phase transition. Okay? So it's purely, what I will say now is purely mathematical. Okay, so first I take the case, it's not exactly the Big Bang, because I take a manifold with boundary, that is a closed ball. And at T, it's a ball with a radius which grows linearly with respect to the time. Then associated to it, you have the constant shift on the cone T positive. Okay, and you ask how to extend this closed cone for T negative. So a first idea is to take the opposite closed cone, but it's not a very good idea, because if you look at the cone macrolocally, that is, if you look at the macro support of the constant shift on the closed cone, then the closed cone is the interior conormal. And if I extend the interior conormal, as in the picture, I find the exterior conormal. And the exterior conormal means the macro support of the constant shift on the open cone. So to extend naturally the closed cone, we find the open cone. But if you want to glue the open cone on the closed cone, it's not so obvious. And in fact, one can construct what is called a distinguished triangle between the closed, which goes from the open cone shifted by the dimension on some inside some candidate K, and for T positive, the closed cone. And this construction was done by with Guillermo and Kashiwara. So we see that the natural extension of the closed cone is the open cone shifted by the dimension of the space. And, but here is balls with boundary, but we can do the same more generally, because here we have done nothing but the quantization of the Hamiltonian isotopy. We start with the conormal to 0 in Rn and use the Hamiltonian isotopy to x psi associate x minus t psi over norm of psi. It's a Lagrangian, it's a Hamiltonian isotopy on the macro support of K, which is a constant sheaf, the sheaf associated to this isotopy. The macro support of this sheaf is smooth, including above the zero section. Okay, but it is smooth. But when you project this smooth manifold lambda on M, the rank of the projection split, change, and that makes the singularity at 0. Okay, but if you take the conormal to the cone, it's a smooth Lagrangian manifold outside the zero section. Okay, so so it's a general, it's familiar to the physicist, this kind of phase transition. And if we work on a Riemannian manifold, here on the example on the sphere, Riemannian sphere, we can do the same. We start with the north pole, and it grows as in blue with the interior conormal. And when the blue joined the south pole, then after we go back, and now we find the exterior conormal. And if we start with the constant shift, when you pass the south, you get a shift, the dimension, I don't remember which dimension, and you can do that at infinity. That is a periodic Big Bang, Penrose like periodic Big Bang. That's a good example. And I think it's enough for today. Thank you. Okay.
Okay. Thank you, Professor Shapira, for that interesting talk. We have time for a couple of questions. Now participants are allowed now to mute themselves, or you can write your question in the chat.
Non, pas de question. Comment je peux grossir mon truc là?
Yes.
Do I have a question? Duan, you can unmute yourself, please.
Thank you very much, Brian. Okay, Professor Shapira, thank you for your very nice talk. I have a question, especially from the side of microlocal analysis, where there is this theory, right, very well known for the analyzing for analyzing the hyperbolic system, that is the theory of Fourier integral operators, right? I wonder if there is some bridge maybe between this classical theory that comes from microlocal analysis in the sense of Hormander and so on, and this theory that actually you show from the side of algebraic analysis, right? Just as a general question, maybe if you can mention something about this.
You want a bridge with what? With
between this classic theory of Fourier integral operators
okay.
and the theory that you showed.
The bridge has a name, Hermander. But in fact, the theory of general system is only known for D module, for in the analytic case. Okay, there is no theory for infinity differential operators. And as I said, to work with the hyperbolic, the Cauchy problem is well posed with hyperfunction and not well posed for distribution. This is the aim of my talk, in fact. Try to convince you that the language of hyperfunction, in fact, is much adapted to PDE, to analytic, to linear. I speak only on linear PDE. It's perfectly adapted to analytic linear PDE. Okay, but of course there is some price to pay, which is sheaf theory, homological algebra. So for some people it looks enormous price, but if you start from the beginning, there is no functional analysis. So on this side, you can skip all functional analysis and just work with purely algebraic array. Okay, so it's not the same education. So for young people, I encourage them to try to understand this point of view, but of course it's not easy. I agree. And moreover, I work with classical category theory, okay, derived categories, but this is totally old-fashioned. Now people work with infinity category, which is incredibly more difficult than the classical derived categories. Okay.
Thank you very much. Thank you.
Thank you.
Okay, we have another question in the chat from Ruival Santos. Professor Shapira, is it possible to extend for nonlinear equations?
There are people who have done it. In particular, the very well-known Professor Yao, with two collaborators. I forget the name, Sheshmani and I forget the name, Christophe. There are three of them in China. They have written a very difficult paper, extremely difficult paper, but to say the truth, I'm not convinced, because if you take the simplest nonlinear equation, the only equation that I know, f prime equal f squared with one variable, okay? Not very difficult equation, f prime equal f squared. So the solution is 1 over z minus lambda, okay? So you have no propagation. The characteristic, the principal symbol of this equation is f prime, is d over dx, so it cannot be simplest, and there is no propagation. So, so for the moment, I would say that there is a big literature, but nothing which convinced me for nonlinear.
Okay, okay. Thank you, Professor Shapira, again for your talk, for joining us today.
Thank you.
The next talk will be begin now, right?
Yes.
I try to lead. How can I?
Okay. Thank you very much, Brian, for sharing the session of Professor Shapira. Thank you very much, Professor Shapira. So now we invite Professor Luigi Rodino to join the session, and
Hi.
Professor Gianluca. Hi,
Yes.
Professor Rodino.
Thank
how
you
are
for the invitation.
Yeah,
Very
please.
happy to join the activities of Latin America. The program could be the following, that I chat for 5-10 minutes, and then Gianluca project the slides.
Okay, that will be very nice. Maybe I will give just a very short introduction about you for the Latin
Thank you,
American
thank you, thank you.
participants. Yeah, that will be nice. So Gianluca then is going to share the slides, right? Hi, Gianluca.
Hello. Yeah.
Hello,
I will.
Gianluca. Okay,
Can you hear me?
please, maybe when you wish, you can just share the slides of Professor Rodino.
Okay, shall I do it now or after the presentation? Okay, because
Maybe let's check. If you can share them now, that's okay.
sure.
Maybe the
Let me
first
go.
slide. Very good. So then let me introduce Professor Luigi Rodino. Thank you very much to all the participants that are connected. It's really my great pleasure to introduce our next speaker, Professor Luigi Rodino from Italy. So Professor Rodino is very well known in the community of harmonic analysis and partial differential equations, right? Professor Rodino's research spans a wide range of ideas, including harmonic analysis, operator theory, and their applications. Throughout his career, he has published around more than 150 papers. You have written several monographs and edited several volumes. Additionally, he has been involved in international research collaborations, including ones with UNESCO. He also co-served as editor-in-chief with Professor Wong for the Journal of Pseudo-Differential Operators and Applications. Professor Rodino also has held several notable leadership roles, including serving as president of the International Society for Analysis, His Applications and Computations, ISAAC, from 2013 until 2017. So he's widely recognized for his effort to enhance the visibility of mathematical analysis in Italy and worldwide. So it's really my great pleasure that Professor Rodino is with us. Thank you, Gianluca, for sharing the slides of him. And Professor Rodino, when you wish, please start.
Okay, thank you. But before speaking about Wigner, I have a short comment concerning the part of the initial presentation of the president of IMU. It's a delicate question concerning the meeting, the next Congress in US. You know, there were some discussions because some people were not admitted because it didn't receive the visa. So there were objections from some mathematical unions, in particular, I know France and Brazil as well, proposing to move to the next year, the meeting. As for Italian Mathematical Union, they proposed a compromise which is followed, I understand, from the organizers of IMU, that is to allow video participation. Okay, quite difficult. Personally, I was in a committee discussing this for the Italian Mathematical Union, and I joined the proposal of Italian Mathematical Union. Certainly, general philosophy is that it would be good to fix such meetings in a nation where everybody is admitted from any frontiers without problem. And I think, speaking about Latin America would be a good place for in such occasion, not only for mathematics, but say in general for these international, in my opinion, it is a peaceful place, Latin America. So these the places where international discussions are decided, etc., should be there. Okay, but much easier for me to speak about Wigner now. About Wigner, short history. Wigner was from Hungary. He studied with Hilbert in Germany for a short time, and then he moved in the United States. And he was Jewish, and he had to move there, and I think all the time was in Princeton University. And I had a very important charge after the Second World War, was president of the nuclear project of the US. What we are speaking about is the so-called Wigner transform or distribution that appeared in a paper of Wigner in the 1932. So at that moment, quantum mechanics were already born and growing a lot, and in particular, Schrödinger had already proposed his equation, and this was adopted immediately as well by Wigner. What Wigner did in a paper, or in this paper, he proposed this Wigner transform is a joint probability density for, let's say, times or space, according to the application. For Wigner is space and frequencies or momenta in quantum mechanics. So personally, I knew from a long time Wigner transform, but only relatively recently I realized that it was a version, say, a possible version of microlocalization alternative to the Ormander presentation, and in the talk of Pierre Shapira, you have seen a completely also different approach to microlocalization. And this was particularly efficient, this proposal, for the study of Schrödinger equations. Say, it realizes a dream, or which is in well emphasized in the Ormander work, that is, singularities move should be considered microlocally and move along the Hamiltonian flow in the phase space. Very interesting is that after 20 years, Wigner transform was used in signal theory, time frequency analysis. And very curious, interesting is that Wigner distribution is so done that ghost frequencies appear. So in particular, if the initial datum, the wave function at first is a couple of delta at -1 and +1, then Wigner transform emphasizes some ghost frequencies in the middle. This is, of course, is a problem for time frequency analysis, for signal theory, where we should be very clean in -1 and +1 without ghost frequencies. And this is what attracted my attention and also my collaborator, of course, many people around. Okay, I think it is time to give the word to Gianluca Giacchi. He will present the slides.
Okay, so I'm not sure to know who I have to thank now, because I am giving the talk on behalf of Luigi because he couldn't do it. But basically, I'm presenting his very recent work with myself and Elena Cordero. So it's this Wigner analysis that he just described. So let me start from scratch. Okay, so in order for everyone to be set on the same channel, let me start really from scratch. So this is the inversion formula of the Fourier transform with my normalization, with our normalization. So for those of you who are into this semi-classical analysis, I'm choosing h bar equal to 1 over 2 pi. So this formula is clearly telling you that the Fourier transform is a global object. So this fails to describe phenomena like human hearing, where we have a notion of local frequency content. So we can intuitively associate a family of notes around a time of interest x for music signals, for instance. Now, in time frequency analysis, we adopt a phase space perspective, and this is also very common in micro-local analysis, for instance. Basically, the phase space is a model also for the music score. We put the time on the x-axis and the frequencies, the notes, on the y-axis, and we study signals from a phase space perspective. So we study their image through time frequency representations. Now the most common time frequency representation is the short time Fourier transform, which consists of localizing signals around time of interests, say x, through a sliding window. So in this case, you choose a window G that may be a compactly supported function around the origin, the cutoff. You move it around x, you multiply it by f in such a way that you obtain a localization of your sound, your function around x, and then you take the Fourier transform, so you compute the frequencies. This gives rise to the so-called indeed short time Fourier transform, which is very popular both in quantum mechanics and in signal processing. Literally, this is exactly the integral expressed here, which converges for f and g in L2, but we can also define it for temperate distributions, simply interpreting this as a weak integral. The window G is usually chosen by the user that is analyzing the signal. For f in S prime, we simply restrict the possible family of windows to the Schwarz class, and then we test the temperate distribution f against the so-called time frequency shift of the window G in X and psi. This is just the composition of a translation and a modulation. And this is the sesquilinear duality pairing Schwarz prime Schwarz, which extends uniquely the L2 inner product. So now, once we define the short time Fourier transform, we can define nice spaces where we can treat the Fourier transform. You all know that the Fourier transform acts very terribly on Lebesgue spaces, but there are spaces where it actually behaves somehow well. So in order to define these spaces, we take the end time frequency content of a signal simply by computing its short time Fourier transform with respect to a fixed window chosen by the user. It's not important. And then what we can do is computing the LP norm in X, the LQ norm in psi, for instance, so time and frequency Lebesgue norms, but we can also weight the short time Fourier transform with a weight M, which measures the growth or the decay of this signal. Which means in the phase space, which means basically measuring the smoothness of the function in the time domain, so the domain of f. This procedure is summarized by this mixed Lebesgue norm. So you first multiply by the weight, which is positive, then you take the LP norm in X and the LQ norm in psi in the order. These spaces are called modulation spaces. They were defined, so this is a Banach norm on a subspace of S prime. And these spaces were defined by Feitinger in 1983 for the first time. Now we are mainly concerned about polynomial weights. So for instance, this polynomial weight. So I denote by VS the Japanese brackets, okay, so polynomial growing weights. And actually, so I repeated the definition here, modulation spaces include plenty of classical spaces such as L2 weighted by M. This is the space M2, M tensor product with 1. But also Shubin-Sobolev spaces, which are M2VS, potential Sobolev spaces that are simply the classical spaces HS. They are very popular. And they are M2, 1 tensor product VS, but also Hermander classes. It can be proven that Hermander classes are the intersection over positive exponents for the weights of these spaces. In particular, among these spaces, so the ones giving the intersection. So we consider M infinity Q one tensor product Vs. This is a so-called weighted Shostran class, and is a very nice class for symbols of certain Fourier integral operators due to some algebra property, as we shall see. So among all the modulation spaces, actually, I will basically only work on this space with M equal to 0, which basically means that here you have one tensor product Vs. So the weight is this one with M equal to 0. So I would say probably, okay, this one here. But the parameters are infinity, comma Q. Don't look at this picture for the parameters, look at this for the spaces, but here for the weight, M2. Now, the whole rationale of Wigner analysis is performing analysis of operators from a time frequency perspective. So the first class of operators that one thinks when we do harmonic analysis are, for instance, Schrödinger propagators for, say, Schrödinger problems with quadratic Hamiltonians. These are precisely these Cauchy problems. We take an initial datum, say in Schwarz, and the Hamiltonian here is a quadratic phase, with HW being defined as in 6. So you see HW has depends basically on this matrix M, which is symmetric. So the Hamiltonian flow of this equation is a matrix. It's actually a symplectic matrix. I'm not getting into the details here, but it's a symplectic matrix. And the propagator is a one parameter subgroup of a group that is called the metaplectic group. Again, I'm not getting into the details, but they are very popular topics in harmonic analysis. Importantly, we are interested in the fact that the Hamiltonian flow is a one parameter subgroup of invertible matrices, say, and the propagator is a one parameter subgroup of unitary operators on L2. And now this is where it comes Wigner analysis. So as Luigi mentioned, from the original paper of Wigner, we extrapolate the definition of the Wigner transform. The Wigner distribution, the cross-Wigner distribution to be precise, is the polarized version of the Wigner transform, and it is defined as the integral transform here. It's similar to the short-time Fourier transform, but here the translations are symmetric. If f is equal to g, we simply write WF, which is the Wigner transform. And Wigner noticed that you can downgrade Schrödinger equations with real quadratic Hamiltonians to transport equations by applying the Wigner transform. So the Wigner transform is a sort of, maybe the next slide, okay? So this is basically the rationale behind Wigner analysis. The Wigner transform is a sort of fingerprint of functions in the phase space. So if you have a function, you can compute its fingerprint. Then you apply an operator which modifies the function and modifies the fingerprint as well. And you ask yourself, how is this fingerprint modified? And the operator that modifies the fingerprint will be called Wigner operator. And in the case of the propagators of Schrödinger equations with real quadratic Hamiltonians, this is exactly a change of variables with the inverse of the Hamiltonian flow. So say the singularities propagate in terms of the Hamiltonian flow, as Luigi just stated. So this capital K is a change of variables. This is a symplectic change of variables in the case of the propagators of quadratic Schrödinger equations. So I start with the first work of this huge project by Luigi. That is an idea of Luigi. And starting from Fourier integral operators. So we perform Wigner analysis of certain families of operators, starting from Fourier integral operators, and then I will also discuss a more recent work, which is about Wigner analysis of PDEs. So as I told you, we consider Schrödinger problems with initial data in Schwarz, and now the Hamiltonian is now the sum of a quantization of a quadratic polynomial, which is exactly what I described so far, say the Weil quantization. And here we sum a perturbation, and the perturbation has a symbol which is in the modulation space M infinity Q one tensor product Vs of R double D, which is exactly the weighted Shostran class that I tried to illustrate before. So now, type of these equations are, say, the minus Laplacian. So this is kind of Hermite equation, so the quantum harmonic oscillator, where now we take, for instance, minus Laplacian plus qx in a product with x, and then we have a perturbation, for instance, v of x, where capital V is a function in the Shostran class M infinity Q. This is precisely an example of this prototype of, as a prototype of this type of equations. It's not a typo here, you have D, here you have double D, it's correct. Now, generally speaking, it is known that in a neighborhood of the origin, the propagator of this equation can be written as a Fourier integral operator of type 1. And this is an operator of this form, okay? So you take, basically, it's a pseudo-differential operator, but now we consider a more general type of phase functions. And everything here is time-dependent. And it may happen that the time dependence is at some denominator, in which case this integral representation holds only locally around 0, and there may exist times called caustics where this representation fails. And but it holds after the caustics and before the caustics. So it's a piecewise defined propagator, if we like. So we have a sort of similarity with what happens with the description of a circle. If you limit yourself to describe the circle with one independent variable functions, like here, you must split the definition into two parts, right? And no definition holds. Actually, you also need other two parts to complete the atlas, but let us forget about that. So you have 2 points where the expression with these functions fails. However, this is very easy to treat. Okay, these expressions are very easy to treat to study functions. And these are singularities. Here, now we have 2 independent variables, x and y. However, the equation describing the circle is implicit. Here it's explicit, here it is implicit, but we have no singularities. So if we double the number of variables, we take the Wigner transform indeed. You double the number of variables, you agree, because you pass from the variable of a function from the variable of a function, and it's fully transformed the phase space, right? But we don't have singularities anymore in the expression of the circle. Now the circle will be our propagator in our example. So say the Hermite propagator, the quantum harmonic oscillator, where we actually have this problem. And now, just let me recall some definitions. Say capital T, take capital T as a linear and continuous operator from Schwarz to Schwarz prime. Of course, you have the Schwarz kernel. So you know you have a tempered distribution in S prime of R double D, which gives the usual kernel interpretation of the operator. So now if this is an integral, this will be the integral of f against the kernel. Now we simply apply the Wigner transform, basically the cross Wigner distribution. This is fundamental. So not the Wigner WF, but WFG. And the Wigner kernel of capital T. Now I'm writing a Wigner kernel, but I will state its uniqueness in the next slide. So a Wigner kernel for capital T is a tempered distribution in S prime of R for D. So observe that we are doubling the number of variables, such that the same equation as 8 holds, but with the cross-Wigner distribution instead. Observe that we are applying T to both F and G, because we are interested actually in the Wigner transform WTF, but we need the cross-Wigner for the definitions and the proofs. So if the following integral converges by setting indeed the interesting case where F is equal to G, this means that WTF is exactly equal to WF tested against the Wigner kernels. So it's exactly a parallel to the Schwarz kernel setting, but doubling the number of variables. Okay, now you remember the Wigner analysis rational, but there are alternatives to the Wigner analysis that are very known and well established in the literature. So Gabor matrices, for instance. Gabor matrices are essentially the same as considering Gabor Wigner. It's a Wigner analysis with the short time Fourier transform, basically. And the Gabor matrix is is a time frequency representation for operators, right? It's a sort of matrix for operators, infinite dimensional matrix, where constructed not using bases but using frames. So computationally speaking, we are interested in understanding whether this matrix is concentrated or not, say on some manifold, like I don't know, the diagonal. Okay, so if it decays very fast off the diagonal, we are happy because computationally speaking, this operator has low computational costs. And there is a relation between the Gabor matrix and the Wigner kernel. The relation is that the modulus square of the Gabor matrix is the convolution of the Wigner kernel with basically the Wigner transform of the window you choose to analyze your signal, tensor product itself. We need to double the variables here. And so in principle, the Gabor matrix is a smooth function, whereas the Wigner kernel can be a distribution. Another alternative is the Bob quantization, which is very popular in the School of Vienna. For instance, it's very popular. It's studied by Maurice de Gosson, where they apply on capital T only to F, not to G. So they cannot take WTF as we do in the end. Okay, but this is an alternative to both the Gabor matrix analysis and the Wigner analysis. The operator that intertwines the Wigner transform, which exists, and whose, in our case, the Wigner kernel is exactly, I don't know if I wrote it somewhere, no? Okay, basically the Wigner kernel is exactly the kernel of this operator when you also put T here, okay? And this is called the Bob quantization. In our case, we have a sort of Wigner operator. So this is just a repetition for the definition of the Wigner kernel. And as I told you before, the Wigner kernel always exists and it is unique. And we can relate it to the Schwarz kernel of T by these equations. So it is roughly the Wigner transform of the Schwarz kernel, where you swap the two central variables and you change the sign of the last one. Now, the change of the last sign is somehow surprising, but it comes out by computations. And this is basically because we have to, you see here, you have time, frequency, and then you have to arrange them as time, frequency. So it's present because of our choice of notation. And now the first contribution in Wigner analysis, which, let me repeat, it was defined by Wigner, but then it was studied by us, and it was formalized by us. And it's downgrading Fourier integral operators. So the operators expressing locally the propagators of these Schrödinger problems that we consider to pseudo-differential operators, which are Fourier integral operators with fixed phi, x and psi. I haven't told you at the beginning, but this is the definition of a pseudo-differential operator. Now we need it. Just as a byproduct, we basically obtain a representation for Wigner for the propagators, which is specifically the representation provided by the Wigner kernel or the operator corresponding to the Wigner kernel, which is the capital K that basically makes this diagram commutative. So it's the operator obtained by composing these three. That holds also in the caustics. So in the places, in the singularities where the integral representation failed, the Fourier integral representation failed, our representation, the representation with the Wigner kernel, holds. And now the main result, which allows all of this analysis, is the following. So you take now a Fourier integral operator of type 1. Again, it's this type of operators. And I haven't defined exactly the class of symbols and phases, because the symbol will be in our Shostran class, as I told you before. Let me also stress that if you're not familiar with these Shostran classes, which is highly probable, you may just think of this symbol to be smooth, bounded, along with all of its derivatives. It's in the Hermander class S000, which appears in this framework because of its algebra's properties. And the phase function is actually a quadratic phase, like here. It's a quadratic form, like here, which can be related to symplectic matrices. Indeed, this is actually the matrix 2D times 2D, real matrix, which is symplectic. And it is associated with this form. And now it can be proven that the Wigner kernel of this Fourier integral operator is itself a distribution, and it is the Schwarz kernel of a pseudo-differential operator, so a very particular instance of phi, a simpler instance of phi, with symbol in the same class as before. So we preserve the time frequency localization of the symbol, and we downgrade the Fourier integral operators back down to pseudo-differential operators. The only thing is that you have to modify the Wigner kernel. It's not really the Wigner kernel. It's the Wigner kernel up to a small change of variables in the frequency variables. That is a symplectic change of variables, still linear. And yeah, let me stress that the class of operators satisfying this property here, so the class of operators whose Wigner kernel is the Schwarz kernel of a pseudo-differential operator with symbol in this class for a fixed matrix S. If you vary now the possible matrices, you obtain an algebra of operators, a quasi-Banach algebra, because Q can be smaller than 1, and is a Wiener algebra, is a Wiener subalgebra of the bounded operators on L2. So it means that it is inverse closed. Okay, if an operator is invertible as a bounded operator on L2, then its inverse is also an operator satisfying this property. A property that fails for Fourier integral operators of type 1. They do not form an algebra. So this is for the Wigner analysis of fields. Now I will spend some time discussing Wigner analysis for PDEs, which is basically the last work we have written about Wigner analysis. Here we consider PDEs defined in terms of this type of operator. So observe that this is basically polynomial in the time derivatives and in the time. Now there is a dualism of names, because in time frequency analysis, usually this is the time and psi are the frequency. So let me say space. Okay, so in the time derivatives and space derivatives, this is polynomial. The polynomial of degree m for the time derivative, and for the space derivative, there is no constraint on the degree, and the dt of the derivative of order t in time is separated by the others, which are multiplied by an operator in the form ak dx, where ak are polynomials themselves. And here we are denoting with capital D xj, the usual, the rescaled derivative with respect to xj. Now, in this case, the rescaling is done by means of 1 over 2 pi I, because we are fixing h bar equal to 1 over 2 pi. So we consider the Cauchy problems associated with this operator. Well, it is known that the well-posedness of these operators is subordinate to the validity of the so-called Hadamard-Petrovsky condition, which is as follows. So there must exist a constancy positive, so that whenever tau and eta in C cross RD are such that PIT, comma eta is equal to 0, this must imply that the imaginary part of tau is greater or equal than minus C. So let me also mention that this analysis will be performed in the so-called Gelfand-Shilov spaces. Okay, these Gelfand-Shilov classes, for those of you who are not familiar, are simply they are subspaces of Schwarz, where we measure concretely the decay of the derivatives. So we fix two parameters, mu and nu, with under the constraint that mu plus nu must be greater or equal than 1. And we say that a function belongs to S mu nu whenever the derivative of order alpha is controlled by a constant to the power length of alpha, alpha factorial to the power mu, and the power mu appears instead here, where you have e to the minus epsilon mod x to the power 1 over nu. So for instance, if nu is 1 over 2, this is a Gaussian control. And now the solution to the Cauchy problem that you read before can be written, and this is known, as the sum of derivatives of a certain function, capital E, which is time dependent, convolved with this is basically the same polynomial we had before, now tested on the initial data. Here you also have an operator applied to the initial data, of course. And now observe this capital E. This capital E is the inverse Fourier transform with respect to the variable eta of a certain function sigma. And this sigma, this, let me call it symbol, is the unique solution, fundamental solution to the equation that we are considering, to the operator that we consider, the polynomial operator that we consider. And therefore, we can reduce the study of the solutions of the Cauchy problem simply to the study of this sigma, or equivalently this E, okay? So, because it's everything, it's just dependent on this capital E in the end. Now, some example of operators. The wave operator, we know that it's, I will repeat these things also later. It's related basically to the solution of the wave equation has sigma equal to the cardinal sign, this version of the cardinal sign, okay? Up to the t at the denominator, this is the cardinal sign, basically. The Klein-Gordon operator with this symbol, or the heat operator with this symbol here. Now, actually, we work under a stronger condition than the Hadamard-Petrosky condition, which is the following. So we ask not only for the existence of a constant capital C positive, but also of an R greater or equal than 1, such that whenever P of I tau comma Z is equal to 0, so whenever I tau comma Z, sorry, is a 0 for capital P, well, the imaginary part of tau must be greater or equal, not of minus C, but of minus C times a polynomial in the imaginary part of Z, which is 1 plus mod of the imaginary part of Z, everything to the power R. This is stronger than the Hadamard-Petrosky condition itself. And now, in the literature, also by Luigi, under this stronger condition, we know that the symbol of the operator we are studying, so remember that this is exactly the operator we reduced ourselves to study, satisfies some decay estimate of Gelfand-Shillop type. You can read it here from 28. And in particular, observe that if R is greater or equal than 1, then mu must be smaller than 1 because the sum must be greater or equal than. No, sorry, I am got confused here. No, okay, this is just another thing. Sorry, let me skip it. So now, from the Gabor matrix perspective, as I told you, in the applications, we are interested in the decay of the Gabor matrix because it's like having nice computational properties. And here we are quantifying everything by means of these parameters S and epsilon actually is also quantifying everything. So under the strong Hadamard-Petrosky condition, by setting S as the maximum between 1/2 and 1 minus 1 over R and choosing G in the Gelfand-Shillop class S as S over D, then the Gabor matrix of an operator satisfying this assumption decays exponentially outside of the diagonal. So it becomes very small, the matrix becomes very small outside of the diagonal. Now, actually, epsilon and S are time dependent, and the dependence depend, of course, on the operators that you are considering. So, some example. So if capital P is hyperbolic with respect to T, then the SHP condition is satisfied with R equal to 1. And if we choose the window, basically a Gaussian window, then recall that 1/2 is associated with Gaussian behaviors, then sigma, the symbol of the evolution, basically satisfies this decay. Its Gabor matrix satisfies this very nice Gaussian of diagonal decay. Second example, yes, for some epsilon positive. Now, a second example, which includes basically the heat operator, we consider this, say, the powers of the Laplacian plus the derivative with respect to t, which satisfy the SHP condition for R equal to k. And if we choose S equal to 1 minus 1 over 2k and G in SSS, then we have this exponential decay of the diagonal of the phase space again. And now we studied the case where sigma has a symbol in S mu nu, where mu is greater or equal than 0 and nu is greater or equal than 1/2. By choosing G in the Gelfand-Cheilov space, let me state that this is basically related on the decay of a function and its Fourier transform. So this means that G decays as e to the minus something mod x to the power 1 over s, and the Fourier transform of G does the same. So every condition we are putting on these weights is simply because by the standard uncertainty principles, like Hardy's uncertainty principles, we have constraint on the joint decay of G and its Fourier transform. So the Gelfand-Cheilov classes may be empty for some values of the parameters. So if we choose S to the maximum between nu and 1/2. Now, if nu is infinity, we have this exponential decay for the Gabor matrix. If nu is greater or equal than 1/2, then we have this other decay for the Gabor matrix where the frequency variables behave differently with respect to the time variables. Okay, here Z is x psi and W is y eta in R double D, and this will be a notation that I will use throughout the remaining part of the presentation. Here, rho, by the way, is the minimum between the inverses of nu and nu. So we have, I would say, exponentially, indeed, exponentially accurate localization in frequencies. Now let me focus on the complex heat equation. So I take the complex heat equation means that gamma here is a complex number with positive semi-definite real part. The initial datum now can be thought, say, in parts for simplicity. So now the solution is a Fourier multiplier. And the symbol is this one. So it's a Gaussian symbol. So it's in S 1/2, 1/2. And therefore, an application of our result gives exactly this decay. So we have the nice decay in frequencies and the off-diagonal decay in the time variable. Now, to be more precise, let me give you some explicit estimates of the Gabor matrix. So recall that Gabor estimates for the Gabor matrix and estimates for the Wigner kernels are basically the same thing up to a convolution, okay? So for alpha positive and T positive, of course, estimates for the Wigner kernels are difficult simply because the Wigner kernel can be a distribution. So we need the convolution, indeed, to get some function. So now in the complex heat equation, now let me assume alpha positive. And you can define this epsilon and the constant C as written here. Okay, I'm not reading the definitions. You see how they are time dependent from alpha and beta. Now, the Gabor matrix with Gaussian window, of course, because we are in a situation where the window must be taken in S 1/2, 1/2, satisfies this decay. So sorry, this is epsilon divided by 2. It's a typo. And here, this is a sharper than the general estimate we had before. And this is the sharp estimate for the heat equation. Well, okay, then observe that epsilon is always less or equal than pi/4. This is for sure, and epsilon is exactly equal to pi/4 when beta is 0 and the time is 1 over 2 pi alpha. Now some picture, okay? So we plotted the Gabor matrix for z equal to 0. So the first point is 0 and the second point is in R2. So this is the estimate that we obtain, and this is the estimate of our result. But the sharp one is different, as you can see. Okay, so our estimate captures it's general, so it will not be sharp, but captures an anisotropy that is actually present somehow. Okay, so we are now letting evolve the system, like here actually, but you see here that there is a stretching also that is due to the dispersive nature of the operator. Okay, let me now conclude with the Wigner analysis of the wave equation. So in the case of the wave equation, the propagator is slightly more difficult, but it depends on this capital TT. Okay, so the fundamental operator of this equation that we need to consider is this one, which has a symbol which is a certain multiple of the cardinal sign, time-dependent multiple, which satisfies this estimate, and it is therefore for every t, sigma t dot is in S0 infinity. Now, capital P is strictly hyperbolic, and it satisfies the SHP condition with R equal 1. This is something I already told you at the beginning. And our result is then satisfied with mu equals 0 and S equal 1/2, and in case it gives this very nice off-diagonal Gaussian decay. Now, as I tried to recall briefly before, the Wigner kernel and the Gabor matrix are related by convolution, basically. Okay, so the window G used for this analysis reflects on how the two are related by formula 47. And now by taking a Gaussian window, this formula simplifies as the convolution of the Wigner kernel with capital phi, where capital phi is this is a tensor product of W phi and W phi. And this is a Gaussian. So it's a convolution with a Gaussian. Now, the propagator of the wave equation for dimension less or equal than 3 admits a convolution expression where mt is a positive function, and it is supported on the ball of radius t. It is indeed, the Wigner kernel can be computed explicitly, and it has this form. It can be computed explicitly either by direct computation or by using the formula that relates the Wigner kernel to the Schwarz kernel that I told you before. They are basically one, the Wigner transform of the other. And this is indeed the expression of the Wigner kernel. This is the Wigner transform of this measure. And now explicitly, we have three scenarios. In case d equal 1, the Wigner kernel has this expression. So you have a concentration along the frequency, along the diagonal of the frequencies, and on a cylinder around the diagonal in the time variable. And then you have these, again, sort of cardinal sign behavior. So sign divided by something. This is what I mean. And now for what it follows, let me set S as the difference between X and Y for simplicity, S hat as the S divided by the mod of S for S non-zero, and Xi, let us divide Xi by its parallel component and perpendicular component. When I say parallel, I say along the direction of S hat. And also let me call Rs as the square root of t squared minus mod of S squared divided by 4. And now, in case d equal 2, this is, sorry, type again, this is k. K of x psi y eta is, again, the delta of eta minus xi, kappa t2, where kappa t2 is this function, which depends, again, on which is concentrated on a cylinder around 2 times the time. Sorry, around the diagonal, and the amplitude is 2 times the time. And this J0 is the Bessel function. And this is basically the same situation in 3-dimensional case. What it changes here are the constants. Basically, observe that you also have a dependence on time at the denominator. Okay, the Gabor matrix for the wave equation can be computed explicitly, and it has this integral expression. In particular, we can infer the decay for the propagator capital TT, which is, again, a decay very nicely concentrated around this time, around time and frequencies as well, Gaussian concentration. This I is simply, so these are constants. There is a constant CT here, which depends on basically I is the norm infinity of the integral that you read in the square brackets without the exponential term times the volume of the ball and then a term in time. And graphically, we have that this is the Gabor matrix again plotted for z equals 0 indeed. Okay, so x and psi equal to 0 here. And you see this propagation effect also from a Gabor matrix perspective. So with this, I end my talk. I thank you very much for the presentation, actually Luigi's talk. And I will answer the questions, or Luigi maybe also will be able to do it. Thank you.
Okay. Thank you very much, Gianluca, for the very nice talk. in your joint talk with Professor Luigi Rodino. So at this moment, then we are open for questions. Remember that if someone has a question, then you just need to raise your hand. Or you can write your question in the chat.
So excuse me, I have a question.
Please.
Right. Thank you for the nice talk. I have the next question. Are there important differences between using the Wigner transform for the Schrödinger equation and for the heat or wave equations?
You mean the Wigner kernel?
Yeah.
So you mean these interpretations?
Yeah, the Wigner transform.
I would say they are of the same type. What you see here is that for the complex propagator, you have a Gaussian decay due to dispersion in the frequency variables. So in the frequency variables, you are Gaussianly decaying. You don't have concentration along a manifold in this case. Instead, in the wave equation, here, you have concentration both in time and frequency. So these two scenarios are completely different. And it is basically really due to the dispersive nature of the heat equation, of the complex heat equation in general. Okay, I would say that the greatest difference is here. I don't know if this satisfies your...
Thank you. Yeah. Thank you so much.
Thank you very much, Karina, for the question.
Whereas for is not so, sometimes not so good. The results are not so clear, so beautiful for wave equation.
Okay.
Let me answer. I have seen a question on mail here. Yes, about extension to complex Fourier integral operators. But it will be very interesting, and I think we as far and of course there are
Okay, thank you very much to Professor Rodino. Actually, he just answered the question of Andrea Hurtado, right? About if you have considered the case of the Gabor matrix for Fourier integral operator with complex phases, right?
Sorry, I couldn't hear Luigi's answer. Maybe.
Sorry. So I don't know. No, my as for Fourier integral with complex phase, we have not yet studied them, despite it would be interesting for applications to PDEs.
Of course, we studied the case of quadratic phases, but for quadratic Hamiltonians, complex quadratic Hamiltonians, though, these are included in the analysis. But quadratic phases, they are sometimes included, right?
Right.
Yes.
It seems also that Andrea's question was posed in the setting of Mellin and Egostran theory of Fourier integral operator, right?
Yes. Mellin Sjöstrand had a nice general theory, but they refer, say, mainly the setting. There are many contributions in these last 5 years concerning Schrödinger with real and complex, mixed real complex Hamiltonians, including simultaneously Schrödinger, classical Schrödinger and heat equation, and mixture of these two types. For Gabor matrix, there are many papers, and this is was done, and the terms of the results were the so-called Gabor wavefront set. Whereas for Wigner, I think this is not yet done. Yes, of course, this not only, say, Melin Schustrand, but already Ormander all times did a lot on, they call Meyer representation of as the link with metaplectic operators, with complex metaplectic operators, considered as a solution of these complex valued Schrödinger equations.
Thank you very much, Professor Rodino. I don't know if Gianluca wants to add something. Are there more questions for Gianluca and for Professor Rodino? Okay. If not, then let's thank Professor Rodino and Professor Chiaki for the very nice talk. It was nice
Thank
to
you
have
very much.
microlocal analysis with us. Time frequency analysis.
Thank you.
Thank you a lot.
Very good. So after this very nice talk, the plenary talk of Professor Luigi Rodino, we're going to have a break of 1 hour. So let's then meet in 1 hour at 19 in Central European Summer Time, at 12 in Colombian time. So thank you very much.
Hola, Duvan.
Hello.
Hello. Is the same link for in the afternoon? Yes, is it okay?
Yes, Professor Pacifico, is the same link?
Okay.
It's
So
the
I
same link.
can leave and then return after.
Yeah. Thank you
Okay.
very much for joining us.
Okay, thank you.
Okay, thank you very much. I would like to thank to the participants that are following us. We're going to continue with some information about ICMAM Latin America, which actually is the session that we call the ICMAM presentation 2026. But I really would like to encourage that to the participants that are connected to follow us in the next session of Professor Robinson dos Santos, who actually is senior editor of Springer, who will share about information about different series of books in Springer that in some sense are related with Latin America, right? So the ICMAM presentation has the idea of introducing some new participants, people that are not familiar with ICMAM Latin America, and allow them to know different programs that we have in our organization. So the plan, we start maybe then presenting what is our mission in ICMAM Latin America. So we have different programs, different editorial projects, conference, and so on, that operates, recognizing UMALCA, which actually is the Latin American Mathematical Union, has the highest authority in the region, right? Our mission divides into three main goals, right? The first one is to build a stronger mathematical community. So this is why we organize different conferences and so on, and we are very active in the organization, especially of conferences, virtual conference that allow us to include different mathematical community, including the mathematical community in Central America. So later I will going to talk about a project, a special project that we have in Central America and the Caribbean, but also we are trying to route our partnerships with different mathematical communities beyond Latin America. That's why also this year we start a new project of mathematical conference in Africa that we call ICMAM Africa. Later I will talk about this. Our second goal is to, in some sense, organize scenarios where we can, in some sense, inspire the next generation of women in mathematics. So there has been several activities dedicated especially for women mathematicians, different conference for women mathematicians. The last goal is to, in some sense, leave a legacy in mathematical research. So, in some sense, related to the different conferences and programs that we have in ICMAM, we have dedicated a editorial project with the Springer, and then we start from 4 years ago, publishing different books, a series of books with the Springer, with the goal of providing in some sense visibility for young mathematicians, right? So let me introduce to you also the ICMAM Executive Committee. Essentially here you have members of our organization that have some leading roles inside of our community. For instance, Karina Navarro Gonzalez and Brian Grajales, who actually were present today in the opening ceremony, and also Andrea Hurtado and Pedro Fernandez, who were chairing today the session of Professor Jin Ha and also the session of Professor Shapira, right? So maybe I really invite you to follow our website, right? Then I am going to present with you our website. So here you will find, you can find very easily our website in Google, right? That actually show you all the different activities that we have ICMAM Latin America today has two main institutions where we operate. The first one is Universidad Pedagógica y Tecnológica de Colombia, UPTC, which is an university in Colombia, hosted in Duitama. In that university, ICMAM Latin America has the figure of one research group that is in some sense affiliated with the Minister of Science and Technology of Colombia, and also Universidad del Valle, which is the university where ICMAM Latin America was born, right? So here, when you enter to our website, you have different, you will see the different activities that we have. You can have information about our publications that I will mention. I will mention more information about this later. How to join our community. Usually we have a WhatsApp group and also a list of members of our community where we share information not only about ICMAM conference, but also about different activities, mathematical activities in our community. Here you will see also how to submit manuscripts to the Springer book series of ICMAM Latin America, right? As I mentioned, how to join our community, different programs, in particular the program of young researchers at ICMAM Latin America. If you are, let's say, a young researcher and you are in, let's say, you are a PhD student or a postdoc or even a professor, you can organize a conference with ICMAM and you can submit your proposal using this link here in our website. A link here also is available to see the different open calls that we have in ICMAM Latin America of our, in particular, our series of books. Something that is important is that if you want to have information about different mathematical activities from Latin America, you can also use this link here that allow you to make the registration, to receive information, right, about the newsletter of UMALCA, the Latin American Mathematical Union. It's very easy to be registered in this for this newsletter. You just complete the details that appear in this Google form. Then you will receive information of many activities. As I told you before, you can join us by WhatsApp using this link here. You can have information about partnerships with other societies, for instance, with ICMAM Africa, which is a new society that start working this year. Actually, there is a huge community of mathematicians from Africa that follow also our activities. Then it was natural to open this branch with different mathematical societies in Africa. So you will see information there about people that are working for this organization. You will see here, for instance, a conference that will be organized by ICMAM Africa. The next conference that will be organized on October, the 27th until the 30th of October of this year. You will see that in the same spirit of a different ICMAM conference, ICMAM Africa will try to organize also outstanding conference, inviting outstanding mathematicians. For October, we are going to have the participation of the Abel Prize, Avi Wigderson, and very nice mathematicians. Actually, Jung-Ha, who was with us today, also will be a speaker in that conference. Alan Greenleaf, Professor Pierre-Louis Lyons, who got the Fields medals for his contributions to partial differential equations. Larry Good, Andrea Seeger, Alessio Figali, who actually got the Fields medal, Michael Ruchansky. Authorities of the highest level like Rushan Sang here, Yunan Yang, Professor Joaquin Toff, who actually is president of ISAAC, the International Society for Analysis, Its Applications and Computations, and who also will give a speech in our closing ceremony. and Hugo Dominil Cupan, who actually got the Fields medals in recent times, and many other mathematicians that you will see there that in some sense have contributed to the state of the art of mathematics and that can share with us, of course, very, very interesting topics. So you will see there different people from Africa. I will mention Frederick Opoku from Ghana, Deborah Amani, also from Africa, and different people here that are working very hard for the organization of this conference. This is, in some sense, a counterpart of our Latin American conference, but in Africa, that also will have a dedicated editorial project. So I really invite all of you to not only to follow our conference this week, that is especially focused on Latin America, but also to follow this conference that is focused on African countries. So I also invite you to follow the Latin American Seminar of Mathematics, who actually is the UMALCA ICMAM seminar. It's a seminar of mathematics that by the first time joined our two Latin American societies, UMALCA and ICMAM. You will see, for instance, today at 4 p.m. in Mexico time, 5 p.m. in Colombian time, and 7 p.m. in Brazilian time, the talk of Professor Juanita Pinzón Caicedo, right? And you will see there the list of different speakers. All the speakers, actually the talks of all of these speakers are available on YouTube. You can follow just the website of the seminar, and you will see also there the people in charge. For instance, Professor Brian Grajales, who is one of our ICMAM authorities in Brazil, Andrés Astaiza, who actually is one of the editors of Analysis and Partial Differential Equations in ICMAM, Manuel Martinez, who actually was affiliated to our program of young mathematicians inside of ICMAM Latin America, Andrea Hurtado, who actually is our Vice Scientific Director, and also Fabiola Manjarres and Leonardo Ignacio Martinez Sandoval from Mexico, right? So if you are a young mathematician and maybe you want to connect with other mathematicians from Latin America that are doing very nice research, please follow this seminar. They are doing really a very good job. Maybe also I invite to the people that follow us from Central America and the Caribbean to follow also our activities there. There is a branch of ICMAM Latin America that is especially dedicated to organize conference in Central America and to work for the visibility of this region. Actually, recently we have published one of our ICMAM books that is called, the title is Mathematics in the Caribbean, that actually was very focused in giving a perspective of the mathematical research of the Caribbean part. So here you will see this website is in Spanish. So if you are a young mathematician, especially from El Salvador, from Honduras, from this part of our region, I really encourage you to follow the activities there, especially I think more focus for Central America and the Caribbean. Usually people can apply for funding in the organization of conferences, and we will, in ICMAM Latin America, and we would like to support, of course, different activities there. In the past, we support few conferences that were organized in that region. For instance, one EMALCA school that was organized in Honduras. So I really encourage you to visit this website and to see different activities there. About open calls, remember we have this website, we have this site dedicated to offering information about open calls of our editorial project. At this moment, for instance, we have an open call receiving articles in analysis and partial differential equations. There will be an approaching deadline of 20th of August of 2026. Please have a look to this open call if you want to contribute to our Springer editorial project. There, for instance, we have very nice mathematicians from Colombia that are helping with this editorial project. For instance, Jose Raúl Quintero from Colombia, who got many years ago the National Prize of Mathematics. Julio Delgado, who was professor in Imperial College London during a long time, and Fernando Gallego, professor of the National University of Colombia, and Andrés Astaiza. Please have a look to this information if you want to contribute with articles in analysis and partial differential equations. There are also other open calls here that you can have a look, or you can have a look. For instance, there is an open call actually dedicated to papers that in some sense has some interplays with different disciplines. For instance, analysis, algebra, and logic. So here we have, for instance, as editor to Lara Osinger from Mexico, who actually got recently the Umalca Prize. Professor Andrés Villaveses, who actually is very worldwide recognized for his work in logic. Especially, he's part of the very active community of logic in Bogota, in Colombia. And also you will see here also editing this book, Karina Navarro Gonzalez, the president of ICMAM, right? So please have a look if you are interested in contribute to these topics, especially if you, for instance, if you are a PhD student or a postdoc and you want to have the experience of publishing your first papers, we will be delighted to receive not only your contributions, but also to provide you a feedback in a very human way, giving you also the opportunity not only to have a report from a specialist in mathematics, but also to edit your contribution in order that could be accepted for publication in the ICMAM series of our books. Also, there will be an open call dedicated especially for Colombia. Is this volume, Mathematics in Colombia, Volume 1. There you will see very good Colombian mathematicians, for instance, Alfonso Castro from USA, Jorge Cosio, Bernardo Uribe, and also Diego Alejandro Muñoz, who actually they are in Colombia very well recognized by our community, and also Professor Giancarlos Cortizos from Universidad de los Andes, who works in differential geometry. So you want to contribute, if you are Colombian and you want to contribute with papers, remember here you will have the instructions. You can submit papers, original papers, original research or surveys in applied and industrial mathematics, differential geometry, or in analysis and partial differential equations. We will be very happy to receive your contributions. So there you will have, you will see maybe information not only of, also information of previous volumes. For instance, this volume about differential geometry in Latin America. This is one of our recent titles. Brian Grajales actually is the editor that is handling this series of books that will be active in ICMAM Latin America now and in the future also. This was somehow one open call that was active until February of this year, but that to my understanding next year or or something will be, this open call will be open again for the conference, Differential Geometry in Latin America that Brian organized, and for sure later you will have also the opportunity to contribute to this volume, right? So maybe this is information that I can provide about our open calls of the editorial project of ICMAM. Our website also has a page in Spanish where we explain also our programs and our projects. The list of all the people that in some sense are related to ICMAM Latin America, in particular organizers of conferences and different editors of our volumes also are here. It was very interesting because this year, ICMAM Latin America, thanks to ICMAM Latin America, the Colombian Mathematical Society by first time will publish one volume with the Springer that also is part of our scientific agreement with the Springer. So about previous publications, you can see here our website, and you can go to this part where we put information of all of our volumes that are published. So as I told you before, our last title that was published was this Mathematics in the Caribbean, and you will see there the list of editors, in particular the editors from Central America that were related to this volume, and also other titles that we have in the past. For instance, I really invite you to follow this book about women in mathematics in Latin America, where you will see the list of different women that have contributed with very nice articles to our series, right? So it's very nice to have, of course, this project with us. And we expect to have this project also, Women in Mathematics in Latin America, active in the future. And actually, it will be Karina Navarro Gonzalez, the responsible of this project and the editor in charge of this title in the future. So remember that all our ICMAM conferences are, in some sense, we have all the information of our ICMAM conference here, right? Because, as you know, our conferences are, several of them have been hosted in virtual way. So you will have the information of all our talks on YouTube, and in the website, you will see the link to the YouTube videos of our conferences. Especially from this year, we have had a new we have had new research projects in ICMAM Latin America, right? That are related with our Springer book series that I mentioned before, but also with our early career group, right? Remember that if you are a young researcher from Latin America and you want to be in some sense related with ICMAM, if you want to organize conference and you are a young mathematician, especially this call is especially for young people, we will be happy to receive your application. You just for the application, you just can't write an email, not only to me, but to any authority of ICMAM Latin America. You can write to Karina Navarro, to Ryan Grajales, or Pedro Fernandez Espinosa, and we will be happy to receive your application. And application is very simple. You just need to express your interest in being part of our research group of young mathematicians. And after receiving your email, we are going to try to schedule one interview with you, which actually is just a formality. It's just to know how ICMAM can, in some sense, add value to your career. And then we will happy to have you as member of our group of young researchers. So, for instance, we provide support or perspective for the students who wants to apply for PhD in Latin America, for postdoc, who wants to take maybe decisions about your mathematical career, about how to apply to different positions and so on. We will be happy to to support you in your process of application to different programs. Here you will see Andrea Vanessa, for instance, Andrea Vanessa Hurtado Quiseno, who actually entered to our group from 2025. This year is the Vice Scientific Director of our research community. So this is an example that people that usually takes part of our research group, also ICMAM research group for young people, also can acquire with the time different roles of leadership in our organization, right? So as I mentioned you before, we have the project of women mathematicians. So Karina will be in charge of this project because, as I mentioned, we want to support different activities from Colombia and from other countries in Latin America. We have created this Applied and Industrial Mathematics Division, who actually is a partnership in order to have the publication now and in the future, the book of memoirs of the Congress of Applied and Industrial Mathematics in Colombia. Then you will see, for instance, the website of the past conference that was organized this year in Cali, in Colombia, and the first Springer book that will appear related to this conference in our website of ICMAM in the next months, we hope. There are also here, for instance, two research groups until now that are active, the one in analysis and partial differential equations, and another group in operator theory with different chairs that are authorities in ICMAM Latin America. For instance, I am hosting this, I am the chair of this group, research group of analysis and partial differential equations, where several people not only from Latin America, but also around the world have joined the research group. And with them, actually, we are working in different research projects in analysis, in partial differential equations, in control theory, in microlocal analysis, in differential geometry, aspects of differential geometry related to analysis, so geometric analysis, for instance. So you will see different members of the research group. Also, if you want to be part of the research group of operator theory, where Karina Navarro Gonzalez is the chair and has the support of other colleagues of ISAC, for instance, of the International Society for Analysis, Its Applications and Computation. You will see here, you can write Karina. Also, Brian Grajales will open very soon. Will be in charge of the research group of differential geometry in Latin America. So if you are interested in working with him or in problems related to differential geometry, you can write to Brian. And probably he's not here in the website, but you know, Pedro Fernandez Espinosa is our scientific director now. He works in algebra, combinatorics, and number theory. If you want to work in that area, you can work with Pedro. You can email him and to see how you can establish cooperation. Remember that one of the main motivations in ICMAM Latin America is to provide, in some sense, recognition to mathematicians from Latin America that, in some sense, have contributed not only to mathematics, but also to our research, to our mathematical community. So ICMAM, in ICMAM Latin America, we provide this prize, the ICMAM prize. Actually, Carlos Koenig was our past winner of the ICMAM prize in 2024, and in 2022, we award Tatiana Toro this prize, who actually now is the Vice President of the International Mathematical Union. I invite you to follow our closing ceremony, especially because in the closing ceremony, we will know who will be the winner of the ICMAM Prize 2026. I really invite you to a closing ceremony for this aspect. Also remember that if you are a mathematician from Latin America and you consider that you have, in some sense, that you have contributed to the mathematical community and also that you have outstanding research in mathematics, you can also apply it even by yourself, of colleagues, and apply on behalf of other colleagues, right, to the ICMAM Global Suite Award, right? Please have a look to this prize because, as I mentioned, self-nominations are allowed for this. Then please have a look. This is somehow a new prize in ICMAM. Our past winner was Professor Sergio Rasbaum from Mexico. I really invite you not only to apply by yourself to this prize, if you consider that you have provided, you have obtained very good mathematical research in recent years, but also if you want to have a look, for instance, to the talk of Professor Rasbaum, a very inspiring talk, I really encourage you to have a look to this. And I think more or less all the information that I wanted to share with you, I have given already. Remember, we have the newsletter of Humalca. ICMAM Latin America is helping with in the editorial project of the newsletter of Humalca. So here you will see different people from ICMAM Latin America that is helping with this editorial project. And I think that's all. I really would like to thanks to all of you who have connected, maybe to hear about ICMAM Latin America if you were not familiar. And thank you very much. I think our next talk will be by Robinson dos Santos, who is senior editor of Springer, and it will be in 30 minutes. So in Central European Summer Time, see you on 20, right? It will be 1 p.m. in Colombian time. So I will stop sharing, and if you on the middle, if you have questions in English or in Spanish, you can make your questions, and I will be happy to answer them. Thank you very much.
One,
Dime.
there are some questions in the chat.
So someone is asking, Pawan Kumar is asking, can we submit paper related to applications of differential equations, particularly from Eurasia? Of course you can do it. You can submit your papers and we will be happy to send your paper to continue with the referee process of your paper, revision process of your paper. So you cannot only do that, but we encourage you to do that, Professor Kumar. Okay. Okay, thank you very much. So see you then in half an hour in the talk of the editor of Springer, Professor Robinson dos Santos. So just an information that I received on the meantime that Karina Navarro and Andrea Vanessa Hurtado will organize the Conference of Women Mathematicians the next November 2026. So we invite you to keep pending about this, the open call for this conference, especially for women in Latin America.